All right. Welcome back to EE for everyone. Live again. And I am very excited about that. It has been a long time since we just had a cup of joe and sat down and I had a circuit board to work on. Yep, I'm pretty pumped. I am pretty excited. 4 o'clock, yeah. Oh yeah. Oh yeah. That's crazy. I know we've had some long ones normally open. We've had some long streams, but hopefully this one will go pretty quick. You might notice I'm zoomed in like a madman, and that's because in all the shuffle and all the hustle and bustle and so forth, I happen to misplace the microscope. So we're gonna try to brute force our way towards a microscope. I'll zoom out for a moment so you can see anything. But yeah, we've got this fancy box. Well, it's just a regular box from JLC PCB. Hello, Mr. the Kite Man. Control theory exam. Hello from the Netherlands. Pleasure to have you, man. Pleasure to have you. Oh, yes, control theory. We should have a little bit of that going on. PID compensator. We've got one of those. Got an error amplifier. So we'll dive into some of that. You can almost call this studying. But yeah, we've got our prototypes from JLC PCB and not sponsored. I don't know. I like them. They've treated me well so far. So I guess similar, kind of know what to expect at this point. The pink ball. Actually, before we do this, I want to tell you a little. Sorry for the tease, but there's a little thing that we've been working on that you haven't seen yet, and it's this. This is the rough prototype. For those that are not super familiar with the process, but I think most of you are. Yeah. Oh man, online exams. Basically, this prototype exists for one reason and one reason alone. Because breadboards and dev kits and stitching them together with wires still has a place in this world, and it's kind of the I don't have a prototype sort of place. Where, it's like if you want to do a little bit of software development and make sure the code kind of works so that when you get a board and you assemble it, you can just kind of plop your micro on and hit go. That's kind of what it's for. So these are my buttons, and it kind of sort of works. Just wanted to show you where we came from. But that reminds me. Thank you to everyone in the comments, because y'all shaped this design for sure. This micro selection, the Teensy 4.0. Crazy Laplace transforms. Yeah, so this is Muhammad. This is the Teensy 4.0, and I don't remember who exactly suggested this, but I know they get a shout out in our microcontroller selection video. This is kind of a peek behind the curtain, because there's some design stuff that we've been doing in the background. Obviously, we have a circuit board, and so we're going to be walking through that. But in true EE for everyone fashion, I know that not a whole lot of people end up watching the stream, so it's kind of like I can show the people that are really passionate about this kind of what we're doing, what's going on, and I don't know. It's a lot of fun, so kind of getting ahead of ourselves. But, yep. Yes, this is the Teensy 4.0. It's the reason why we picked it is because what I was really looking for is something that's just a general modular type of form factor that we can put powerful micros on, and I was hoping that we could find a powerful micro from the get-go to put down and try out. And so I looked through, there were a lot of suggestions in the comments, and I know we've used the PSOCs and some of the TI parts and some of the Cypress, I guess those are the PSOCs. We used a lot of different parts, and it's kind of like I didn't really have a strong reason to use any of them, like any micro would really work, so thought we'd try something new, try the Teensy, and this thing screams at, I think it's like 140 megahertz is the core clock. It's got a floating point unit for math acceleration, basically everything I was looking for. So yeah, so thank you for those that shout out. It's not the only change that happened in this schematic. There were a lot of people making suggestions about linear FETs, and well, actually not linear FETs, just regular FETs, and ended up going for that. So we've got a different MOSFET that might be able to pump out a little more power. We've got a few different subtle changes that should get us on a good path. So this is all packed basically as expected from JLC PCB. Doesn't look particularly bad. These all look pretty good. Got 4 of them unpacked. So use their SMT assembly. Again, I'm really starting to love that because, man, if you pick just R's and C's and pretty generic parts, they'll put them on there for basically free. I think it was $3 a board for the parts and assembly, which is insane. Obviously, we've still got some of the specialized components to put on ourselves. The through-hole parts we got to do ourselves. But, yeah, it should be good. I guess none of these look particularly better or worse than the others, other than this one has a manufacturing skid mark. It looks like they left some sticker residue on that one. So I guess not that board is the one that I would prefer to assemble. These both look pretty good. I guess I'll take these two. We'll put the others away for now. Awesome. That'll get us started in a hurry. You might have noticed I grabbed 2 off the pile. I'm going to try to do 2 of these because they really are quick. They're really quick. This is 4-layer Muhammad. So we got 2 inner layers. Those are basically just power and ground planes. Then the outer layers are used for routing. Yeah. Yep. In a slightly different universe, probably could have gotten away with 2 layers. But being honest, I got burned in our last project where we tried to use 2 layers instead of, or we tried to use 4 layers instead of 6, and we really needed 6, and that ended up really biting us because we had some issues with noise coupling into our sensitive nets because we had to have some split planes where we wouldn't have otherwise had split ground planes, and there's high power because it was the UPS, and yeah. So I was like, you know what? There's going to be some current. There's going to be some voltage. I just don't want to risk that. So we got solid ground planes. Yep, and Kicad. Love that tool. If I'm being honest, that tool has really exceeded my expectations in just about every way possible. It's like, I see how much, I see how much some of these tools cost, like Altium and Cadence and Mentor Graphics. I forget what they call it. I think it's DX Designer. Is that what they call their tool now? But it's like, I see these software packages, and they are just like, man, they're expensive. And Kicad is free. And it's like a lot of the free tools that you find online, it's like they're okay, but they're missing critical features like DRCs, like design rule checks, or something of that nature, something fundamental to the process where it's like, you really kind of need design rule checks and net lists and the ability to make libraries and link orderable parts. So just going to zoom in here, see what we can see. All right, which board are we on? It looks like we're on this one. So apologies for the not perfect zoom. Usually we have a little USB microscope that we break out, but like I mentioned, we Altium crashed more than Kicad. Yeah, that doesn't super surprise me. It's like, it's shockingly stable, shockingly powerful, and it's like, you can really get good work done. And it's like, at the end of the day, I see what Kicad can do, and it's like, yes, it's not perfect. Yes, it has some bugginess occasionally, and, sometimes there's a critical feature missing, like the way that you can do microstrips or like transmission lines in the tool, whether that be for RF or for just controlled impedance, and it's not great. Like, it works, but it's not great. So it's like, there's little things like that where there are some advanced features that are missing, but it gets the job done 98% of the time. And so I think for you and me and most things, actually, I mean, it's good enough. It's good enough. Yeah, and 6 layers would be relatively cheap, no corp. In most circumstances, I would agree with you, with one small exception. So these boards, like I said, they came from JLC PCB, got them assembled on their SMT line with their library components and whatnot. And like the fabs are cheap as always because it's from JLC. But these were assembled for $3 a board, parts and labor. And they actually don't do, yeah, most 0 ohms. There's some series 0 ohms in case I need to bodge a different power supply. Like a great example is I decided to keep in the FTDI level translator, and I wasn't sure whether I should tie, well, I wasn't absolutely positive if I should tie VCC back to the micro or if I should let it generate its own 3v3 and just trust that it was going to be tolerant of this region being powered when that one was unpowered for the logic cells. It's like, well, I'll just put a 0 ohm, and if I need to pop off a 0 ohm and run a jumper over to the little VCC pin, that's fine. So most of those are there for debug, where they could be removed. Yeah. Or like if you're looking at these power modules over here, I have 0 ohm that I could replace with an inductor. So you see the way that I routed it kind of like it's a pi filter. So it's a differential mode filter. So if I pop off this 0 ohm and replace it with an inductor or a low ohm resistor, it could prevent noise from coupling back to the 12 volt net. Yeah, I agree. It's really easy to make footprints and symbols in Kicad. It's a great tool. But yeah, so going to 6 layers would mean I can't use this assembly service. And again, not perfect. I know they've got flaws, but $3 a board to get something pretty much fully assembled. It's like, I can solder all these parts to the board, no problem. It just takes forever. Let the pick and place do what it's good at. So it's like going to 6 layer board would not only be a probably a more expensive fab, but also then we'd have to give up their SMT service because right now they only support 2 or 4 layer boards, and I don't know anyone else that's even remotely that cheap and that fast. At any rate, just wanted to give a little walk through of the board. See, that's where the FET goes. Got a little fuse. We got the little buffer circuit up here. So that's our 4 transistor discrete buffer to drive the gate. Talked about, I think that video came out. Here we've got the 4-channel op amp that's running the PID. So this is the P, I, and D terms with the summing amplifier. That's all in this chip. And then we've got U213. I think that says OP07 on it. Yeah, so that's our current sense amplifier. And then we've got a little LDO to give us our 3v3 rail. And over here, no, I'm lost. Sorry, I'm lost. Over here, we've got our comparator for the lockout circuit. So this is the overcurrent protection and the overvoltage protection circuit. What is the difference between all covered ground around the component and normally open total cost is kind of what I was looking at, and man, this was super cheap. What is the difference between the covered ground and the 3 side line ground? I think, did I use a different symbol for the isolated ground versus this ground? So there's actually 2, I'll zoom out for a moment. There's 2 isolated power domains in this board, and there's a great reason why. This is meant to be a piece of equipment that you handle and touch down here, right? There's buttons, there's a screen, there's a USB port, there's stuff that you'd be touching, and The intention is that this electronic load can go up to, well, about 100 volts, and 100 volts DC is dangerous. Like, you can't touch that. You need to keep that isolated. So rather than just flood a ground plane across and have everything coupled to the same net, this is actually, this upper part where you're attaching the load is isolated from this lower half of the board. Should be about 200, 250 volts reinforced insulation, or about a kilovolt of single. So it could probably take around 1,000 volts, but you'd never rate it for that. It's basically around like 100, 200-ish that you'd rate it for. You can see there's that. I just drew a little thing in the silk screen to remind me to not route traces in there. And then digital isolator, isolated power modules. Deliver power up to that part of the design. Yeah. Yeah, great question. Hello, Dave. Welcome. Welcome. So yeah, just kind of finishing up what I wanted to show you on the fab before we start assembling. You can just kind of see the component placement is pretty good. I saw that on a couple of the boards, some of these LDOs were a little crooked. Oh yeah, looks like that one. It's a little crooked, but yeah, it'll work. It'll work. It will work. At least that's what I'm hoping. So, I suppose let's start with the assembly. It's enough fanfare. It's time to get into it. Hopefully everything's working great for you guys. Obviously, we've moved. We're in a new shop. We're in a new place. So hopefully the internet's good and stream's coming through great for you all. Yeah. Yeah. Okay. We are just going to start with the ADCs, because those are probably the finest pitch component. And if I need to wrestle with something, I want to wrestle with this. If I have to wrestle with something, I want to wrestle with this. Yeah, I don't know. So, we'll see how this all works out. But, assuming it goes well, I'd be open to the idea of shipping a couple of these prototypes out to some of our viewers. Would probably still have some assembly required just because I'm missing some components, but whatever state we get these to, and it's been a long time since we tried to do a giveaway of something like this, so yeah, I don't know. I'll ship it as scrap, no guarantees, but I was thinking that maybe we'd send one out to Patreon backer, and I threw a little post out on there. So drop a comment on that post. It's kind of cryptic. I don't really understand how giveaways work. I know that legality can be kind of, yeah, weird. So it's easier if the things that you give away have no monetary value. So, yep, that's why I'll only give away things that are not working or otherwise require assembly. Stream is fine. Good. Good. Oh yeah, Muhammad, we'll do that. So, like I was saying before, this is kind of a look behind the curtain, as it were. So this is, there are a few people that I know that are part of the channel that have a little more experience working with electronics than perhaps some of our other viewers. And so, yeah, I kind of jump ahead and share the exciting moment of assembly with everyone, but circle back to chat more in depth about what we're doing and why. I know I think it was Plant Light Project, or I forget exactly what project it was, but I know that we did a pretty lengthy explanation of what we were doing and why, with regards to layout and best practices and all that nonsense. So I don't know that we'd repeat the whole thing, but maybe someone in the comments has a link they could send you. So that to say, we will talk about it more. I can't promise that it'll be a full, complete tutorial, but we will certainly go back and we'll talk about capturing the schematic and Like we've got some about tuning the compensator, because I did some tuning in LT Spice that hopefully will translate to reality pretty well. Let's see if I can. So we're about to go for that ADC U209. This might get a little ugly. That's not great. You can't really see what I'm doing. Let's try flipping that around. That's much better. Pin 1's in the right orientation. So if my head's getting in the way, I need to see if it's straight. Looks about right. Yeah, looks about right. So I'm going to try to get a little bit of solder on the other side of that chip as well. Clean off the tip of the iron. Come back with some flux, and then just try to drag that solder across the 4 pins. We'll see how many shorts I make in the process. Hopefully not too many. Oh no. No, I always do that. Started with the wrong side of the chip. Knocked it crooked. Come on now. Well, okay. Let's try that again. Wait a minute. Let me pull this off. Take a look. Can I actually bend one of those pins? No, it looks okay. Woo! Yeah, that's yep, that feels like soldering on stream. This brings back the memories. Alright, throw a vote down in the comments. Let me know if you think this chip's gonna survive all the abuse. Alright, alright. Now let's try the side that we didn't just solder down to the board. Huh? Let's be smart. So, for those that are curious, this is a Hazel, or hot air solder leveling finish. Actually went okay. Oh boy, I got way too excited. Sorry, everyone. Framing. This time more art and style. Placement first, then routing. Yeah, agreed. So Muhammad, great question, and normally open, great response. It's like there's a lot of best practices, but it really depends on the application. And like, you know, if you're working with kind of low power designs and you apply all the best practices for like kilowatts, sure, it'll work, but like it'll be way more complicated than it needs to be, and expensive, and it'll be, as I like to say, killing an ant with a sledgehammer. It's like, yes, it'll work, but it might not be the best way. So it's yeah, there's some style, there's some art, whatever you want to call it. But in electronics, there's a lot of absolute right and wrong. There's like the physical physics of electronics, but beyond that, there's some wiggle room. A great example is like signal integrity or like high-speed digital design, specifically PCB design. There's a lot of nuance there, and it occasionally gets skipped or not fully considered. And sometimes you don't do all the math and it still works. Some would say it's luck. Some would say it's even a little reckless. There's different perspectives on how to handle that. PCB routing is much the same. Stabilize. Yeah. Well, I gotta say, it's a lot easier to solder without the camera. Because right now, I'm not even really on top of it. I can barely see what I'm doing. It's less about the PCB being stable and more about having a tripod in the way. Oh boy. Yeah. Way too much solder on this one. That's good. That's good. That's what solder braid's for. Okay. Yeah. We're on 208. You can see the pain. So okay. Yeah, and in some ways, I didn't lay out this board very well for hand assembly of these parts, because I'm just noticing that my iron is like hitting a lot of the resistors and capacitors nearby. It's like I don't have a clean shot on these because this cap and that cap both kind of bump my iron out of the way. But I think that's on. We just need to get the extra solder off the other side. High-speed digital, aluminum foil. Yeah. High-speed digital. It's crazy. And sensitive analog, I would say, is... And that one's a little more cut and dry. You really don't usually have a lot of leeway. Sorry, I wanted to rotate that so that you guys could see what I was doing better, but I literally can't get the iron on it because that cap's in the way. So I'm just putting this across all four leads. Oh no! Guess the other side wasn't soldered down very well, eh? Oh boy. Either that or it was, and I just... No, it was, and I just bent all the leads because I was pushing too hard. Well, that was not great. Oh, yeah. I need like taps or something for those. I don't know what you guys have in your cultures, but that's like the military song when somebody doesn't make it home. I don't know, man. Mechanical abuse can be pretty bad for integrated circuits. I'll solder it back on. We'll see if we get lucky. We might. I mean, one of the most fun things, for those that follow us on Twitter, you might have seen this hilarious, well, I think it's hilarious post. Maybe it's cringy post that we made. It was basically what we did to dev kit or prototype these. There wasn't really a off-the-shelf kit available for testing these parts, but there was just some generic kind of prototype boardy stuff that you could try to solder a part to. And so I sure did. I sure did try, and I actually soldered a surface mount part with the wrong pin pitch onto that board to try to fix it onto our breadboard, and it worked. We got it on our breadboard, even though it was soldered to a breakout board of the wrong pin pitch. I was like, that is insane. That should never happen. But okay. Can't really tell if that's... It looks a little starved on this one side yet, but I am afraid to put more solder on it. I'll do it anyway. Just a little bit on one pin. Clean the iron. And I'm going to try to sweep that across without adding too many shorts. Let's see how that looks. Oh yeah, okay. I'm going to try to get a close-up on those. Thank you for being patient. Okay, let's see if we can focus on that. Okay, so basically just soldered on these two components. This is the one that just kind of went on easy. This is the one where I was really fighting against this cap and that cap. Try to get the iron in there inside of these pins, and this resistor and that cap we're fighting. We're going to try to do. So basically what I should do, if I'm taking notes, is I should rotate C6 and C218 so that they're kind of within this outline. And the same thing for R212 and C, I'm guessing that's 219. Just tuck those in. There's plenty of room. Just tuck them in so they're not in the way. Oh, yeah. So, Muhammad, great question. Yes and yes. Well, I guess, no, I didn't bend it on purpose, but I did bend it. And that's part of my struggle. So, yes, I prefer a J-style tip, but I may or may not have thrown my soldering iron inside of a toolbox, and it may or may not have gotten jostled and bent the tip more than it was supposed to. So the very, very tippy top of this iron is now like bent over. It's in a rough shape. I need a new tip. I need a new soldering iron tip. Yeah. Yep. Yeah, I did get some of those pre-made breakouts. That's what it was. I just didn't. I think it was. I got it assuming that my pin pitch was the same for both parts, but it wasn't. It's like you flip it on one side, is a 10-pin breakout. When I flipped it on one side, it what was the problem on that side? I forget. It was like one side where the pitch was too narrow, and the other side it was too wide. So I just kind of put my tongue at the right angle and hoped. Oh wow, yeah, that one looks better already. And I think I was rusty. It's been a while. How long's it been since the last UPS stream? It's been a minute. We need pin 1 facing back. Oh, so yeah, I think I distracted myself. So, yeah, if you drop a comment on the stream, which, I mean, a lot of you have been, I'll just grab something random afterwards, try to reach out. We've got so one of my frustrations with the YouTube system is, like, if you want to just say thank you to your viewers, send them, like, anything, right? Sticker, blown up FET, literally anything. Just to say thanks for being in the shop. Thanks for spending the time. Thanks for being a part of the community. You know, it's like, that's what I want to do. I just want to be able to say thank you with a couple little things. Because I appreciate you all. I appreciate your time. I love that you're here. And seriously, thank you. Thank you for being here. But it's like, I just want to say thanks. And then we can't even, like, private message through the YouTube platform. It is frustrating. So it's kind of like, I've got to tell you to reach out via email and hope that you can find the business inquiry email. And then, which is really easy, by the way. There's a Google Help article on it. And they do it in a specific way to try to help reduce spam. I'm not sure if it helps or not, but that's what they claim. And, you know, people abuse any system, but it's not my intention. But at any rate, so some of the other platforms that we're on, like we're working on getting a Discord community set up just for everyone. We've got a Slack channel for some of our Patreon members. Well, actually, all of our Patreon members. And through Patreon itself, those all have a direct message mechanism. So that works pretty well. Wow. Was that just a first try? So basically, we'll try to do the whole rigmarole for those on YouTube. And for those on Patreon or Slack, I'll just DM you. Direct message. Okay. Man, did that one just go on? Like first try? That looks pretty good. Yeah, I think that one might have worked. Alright, now let's be smart. Yeah, I don't know what it is about this board, but when I tried to tin the single pin, it just worked a lot better. Dope. Maybe it's the difference of being able to use the flat of the iron versus the tip. Maybe I need to crank up the heat a little bit when I'm using the tip. I'll give it a little boost. It doesn't look much better. And I cannot get that last pin on this part to flow. Alright, let's take a look. Looks... I mean, it might work. It doesn't look great. That still doesn't look great. My goodness. I need to take that capacitor off to put this thing on the... Oh, there we go. There we go. Got it. On the other side, it's much better. A couple of these pins in the middle look a little suspicious. How are these two? That one looks great. That one looks great. All right. Whew. So those are the 4 hardest parts done. That was a little stressful. What's the model? Boards I care about. Yeah, hot air gun. Yep. Yeah, I've got a... Yeah, so the cheap stuff... Yeah, I got a cheap one, and I would definitely recommend cracking it open. I don't have my hot air station here. That's the problem. Yeah, the hot air station would have made quick work of that. Just tin the pads, flux, reflow. That would have been a lot quicker. I got one, and they actually put the fuse on the neutral side instead of the hot side. So like, yikes. Yeah, so I cracked it open, flipped the fuse over to the hot side where it should have been. And yep, electrocution, yep, you gotta, yep. I know one of my buddies, he got a hot air station not too long ago, and he's like, yeah, makes the lights flicker when I turn it on, and I'm like, I don't know how I feel about that. Yep. You are probably the most valuable part of your shop. And yeah, it definitely pays to get quality tools you can trust. Keep in mind that's coming from the guy with the hot air station that he found the fuses on neutral instead of hot, and the soldering iron that he thought might electrocute him, so he had a ground bond to the chassis. So maybe I'm not. Maybe I don't really have a leg to stand on with that. But yeah, there's some good ones out there. But definitely, if you're buying something cheap, crack it open, because you do not know. You simply do not know what you're gonna get. Okay. So we're gonna add in the DAC. ADCs are soldered down. Poor guys. Thankfully, the references are external, so they don't need to go through all that abuse. But yikes. Yeah, if we have a little bit of inexplicable or unexplainable error, pretty sure I didn't follow the reflow profile for those parts. I mean, I'm no expert, but no, I'm pretty sure we didn't follow the reflow profile. Sorry, that was a little bit of a joke. Because, so for those that might not know, all parts, they come, like the data sheet will tell you how to solder them onto a board. Like, it'll actually explicitly lay out how the heat should be applied, what temperature, for how long. That's called the reflow profile. And basically, they say that the data sheet's only valid if you follow that profile for soldering the part onto a board. And it can only go through that profile. I think it's usually once, but whatever amount of times they define is what you can do and still expect the part to meet its data sheet ratings. So that was the joke. Dope. Alright, little solder bridge on that one. Okay, little solder bridge on that one. Those ADCs are tiny 0.5 millimeter pitch parts. Those are not easy to get on by hand. Though with the hot air station, it would go a lot easier. I missed the old lab, guys. I missed the old shop. Like, even just getting this much back together, just getting organized to do the stream, and I got the oscilloscope out, got the soldering iron. Why is that not? Like, doesn't want to reflow. I don't know if it's because I damaged the tip when it was stored improperly or what. Oh, there we go. But it seems like the temperature's running a little cold, which is weird because this is one of those direct heat irons. That shouldn't be a problem, but that really is what it feels like. Okay, one DAC installed. Maybe I'll bump it up just a couple degrees. I'll put it up to 360. Normally run at 345C. If it works, but this is live. Oh, yeah. Yes, Muhammad. So I completely understand that feeling, where it's like, I want to fast forward. And that's part of why I do this. So it's like, you know, we've got a video kind of cadence that we're working on. And so I try to keep a pretty regular flow for all of you. And a part of that is, you know, there's usually a delay, whether it be days or weeks or sometimes months. But yeah, there's a delay between what we're really doing and where the videos are on the channel. And there's gonna be a lot of good little nuggets as we do the stream, a lot of little opportunities to get that back and forth, tips and tricks, like what you're doing, asking questions, and I will address them. I just wanted to soapbox about this for a second. So it's like you kind of get this opportunity to have a little back and forth, more of a conversation, and I love that. But it it ends up being a pretty long format and kind of a struggle for a lot of people to really watch start to finish. So what we'll do after we're done is, I'll kind of take this content, edit it down, and then release it on the channel in a more digestible format, whether it be a time lapse or something of that nature. So yeah, it'll get put in the cadence and come out in line with the story. So you asked another question. Why am I soldering 2 boards? Great question. So you said, why am I soldering 2 boards? If I find a mistake, I might need to fix it twice instead of once. You're right. But if I find a mistake, I'll have something else to compare to. So I can try it on this board, try it on that board, and if one of them works and the other one doesn't, then we know it's probably not a design issue, and it's probably an assembly issue. Like if one of these ADCs doesn't read the voltage right, but the other one does, we know I probably just killed it from applying too much heat. So that is an example. Also, do you not trust me? Do you not trust that the design's gonna work? I'm just joking. Experience of that is not only from friends 50 degrees out. Oh, yeah, it could just be that. But the weird thing is that I've used this iron before, and I do not remember it being this bad. I really just don't. I remember it being much better. Because there were some big ground planes on the UPS project, and that thing just handled it. This is not feeling so good. But just so you guys know, as like, when I was designing this project, I designed it with a slightly different mentality, where normally I'm designing it from the mentality of, I'm going to get the best part, and I'm going to put the best part on the board for all of these parts, and then I'll try to get it assembled, and we'll see what happens. And it's just kind of like that admission from day one of, yeah, sure, I'll kind of half try to make sure it's able to be assembled for cheap and small quantities as a rough prototype. But if push comes to shove, I'll just solder 300 parts to the board by hand. And a big part of this project is like, I'm not just trying to do it. I'm trying to do it in a way that's like sustainable for me and sustainable for the channel. So it's like I want it to be something where I want to make it more accessible, right? I don't want to make people who want to learn more about this type of design, I don't want to make it so you need to solder 300 parts on the board. It's like one of the things that we're starting to do a better job of is, especially for our Patreon backers, when we finish a project like this, and depending on how dangerous it is, we'll release everything like the full Kicad project, or just some details like Gerbers and bombs and stuff. So it requires a little more tinkering. But it's like we're releasing the design documentation on there. But it's like, just in general, an admission that maybe there's a better way to spend my time than soldering 300 parts on a board. Maybe. So it was more committing from day one. This project was more committing on day one, where it's like, nope, I am not going to solder all these parts on the board. 90% of those parts need to be automated, because it's like, otherwise it's just not going to happen. Because, like I said, I don't have all the tools, whatever, lots of reasons. So what I ended up doing is, in Kicad, I started building up my own libraries of parts. And now you can't just throw whatever you want on the board. You still got to be kind of choosy. And so I started building up the library where it's like they've got parts that you can assemble for basically free, and then some parts that are a little more expensive where they charge you like a setup fee that's I think like $3 or $4 per unique type of component. So I was like, well, let's see what I can do with only their basic parts, and then anything more advanced I'll solder by hand. And I was shocked. So it's like, you just pick particular resistor values, and they still got 1% parts, and I picked particular op amps that met our needs, but that were in their library of parts, and I was pleasantly surprised when they weren't like cut rate parts. They're good. They're like ST Micro is one of our op amps. The other one's a TI OP07. It's like, these are not, I mean, maybe they're, I don't want to say they would be counterfeit because LCSC is an authorized distributor, but something like that's always possible, even if it's unlikely. But yeah, so it's kind of like we're just going to try to use that basic parts library and see what happens. So far, I'm loving unwrapping the board and being like, wow, all the regulators are on there, all the voltage references. I wish the rest of those fine pitch parts were on there. I wish we could get ADCs that met our needs. And oh yeah, there was a little discussion a while back. Yeah. Yep. I mean, that's a big part of getting experience, right? It's like, Muhammad asks if I work somewhere. Yep. Yeah, I do. Yeah. Engineer. Yep. So I went to engineering school, work as an engineer, and honestly, I just fell in love with electronics as a hobby. And one of my favorite things about doing projects like this for the channel is that most of the time when I start the project, there's at least one way where I am not 100% certain that I will succeed. Like, there's usually something about the project. In this case, it was using a SPI DAC and ADC. And it was like, I've never really had a reason to do it, and I wanted to try to learn and see what worked well and what didn't. So that was kind of like the thing that I was pushing myself. And it's like, when you do projects like this on the side, when nobody's paying you to design something, you can do some things that might not make total sense. Like, it might not make 100% sense for me to use a SPI ADC for this design. But you know what? If I learn something, I still think it's worthwhile to do that, just for my own learning, so that in the future, maybe there will come a time where like that is the right solution. Like, that's the only way. And when I come to that crossroads, I'll be like, oh, yeah, I've done that before. I've seen that before. And it just enables you to try something new. So that's kind of where this fits in for me. It's like, when I just want to mess around and see if something works, that's when I think it's time to break out. Channel. In this case, there's a couple things. It's that gate driver buffer up here. I'm really excited to dive into that and see how that works. And yeah, some of the other circuits. So hopefully that answers your question. I use this kind of like continuing education for myself. Yeah, hardware design. Muhammad. Yep. This might surprise you, but specifically a focus on analog hardware, not digital. So it's not like a force thing, it's just an interest thing. Maybe a part of the issue that I'm experiencing is the flux, because I'm using a no clean flux, which isn't the problem, but it's like an alcohol-based flux. So maybe it's like I need to burn the alcohol off, and it's like keeping the part too cool. And it's like once the alcohol sizzles away, it seems like it flows really well. So maybe I'm just fighting through that alcohol layer of the flux for a moment. Maybe I need to let that chill. Like let it evaporate before I go in there with the iron. Oh boy, now I've done it. Making all kinds of messes. So putting on one of those serial translators. Got a little too much solder on a couple of pins. Not too bad though. It's the same 0.5 millimeter pitch. Looks great. One more little solder bridge. Alright, a little bit of flux ought to take care of that. It's just the tiniest little whiff of solder left. Beautiful. So the reason why I'm touching that up after the solder bridge is because it can leave little like tin whiskers and little shorts and stuff that might not be obvious. Just want to make sure that I melt any of those down, clear them up. Alright, we're going to leave it so I don't burn the SC out. Let's see, was that everything? I only have one of those, so I can't do it to the other board. U214. Love analog trying to also. Oh. Yeah, I mean, Mohammed, the best way to think about it is everything's got heat, everything's got power. You need a lot of power supplies, and yeah, I mean, there's some cases where analog is just necessary. It's like if you're doing the analog front end for something like voltage measurement, current measurement. Oh, wow, I missed a lot. Yeah, those are banana plugs. Yeah, they screw into the board, basically. So there's vias stitched around it. That's both to support the pads, like mechanically, to crush and or to prevent crushing and things of that nature. Yep. Normally open. Nailed it. Yeah, it's here. I'll save you the trouble. Looks like you're struggling to word. Here it is. These go there. 100% love analog. Yep. Black and red. More vias. Oh yeah. So I mean, one current carrying, of course, that'll help. But it's to prevent from crushing as we turn the screw. So there's physically going to be a screw that adheres. It's not going to be soldered. So when you're doing something like that to a board, sometimes it can help around like standoff holes if you're going to like screw mount a board. But there's different theories. Some people prefer to, let me cut in here. Some people prefer to leave the barrel non-plated when you do this. So leave this unplated. Do the vias around, and then rely on the vias to stitch between layers. Some people plate both. Some people just do a plated hole and don't think about it. So there's different ways. I'm not convinced that one is drastically better or worse than the others. At the end of the day, you're still cranking a screw down onto fiberglass, and at some point it'll crack if you tighten it too much. But maybe it helps. It certainly won't hurt. Yeah, so I believe that we are on to the switches, and then it's through-hole stuff, and then we're done. So we are in pretty good shape. Get this started here. So we're gonna need 7. 7 per board. All right. Did I miscount? Did I drop 8? It looks like 3, 6, 7. Yeah. And then here we got 1, 2. 3. Oh, I think I did okay. Great. Now this will be more normal. So we're just gonna do a more traditional approach to soldering. What about vias on the up? Oh, yeah. So up's labeling the switch, but so that's a heatsink for the linear regulator. So there's a copper pad on the bottom layer of the board as well. So it's stitching heat from the upper to the lower. Really, only the traces right, or the vias right by the regulator. Those are really the only ones that make a appreciable difference. But for thermals, for stitching planes together, that's a different story. But for thermals, the ones right by the pad, or if you can put some in the pad, that's ideal. But vias in pad had other problems. Yeah, SOT 223s. Fernando, great. That's great to have you. Glad you're able to join. Welcome to the stream, everyone who's dropped in. Yes, we are getting close. I'm getting excited. That's maybe the best part about having these mostly assembled, is that once they're delivered, it takes a lot less time to fire them up. What is this, half an hour into the stream? 40 minutes maybe? We're doing good on time. Yeah. So just put a little bit of solder on each of those pads, and now melting it and sliding the switch into position. Pause a moment as the solder hardens. And you're good to go. Now it's tacked in place. We will need to circle back and obviously solder the other lead, but gonna do that on both boards in one big move. Yep, so soldering it this way, it allows you to get everything aligned well. There's only a couple parts that are really, it's like you need to be really, really careful with how much heat you apply. Switches are one of those. Not from like a silicon breaking the part, but it's like you can physically melt the plastic enclosure. Not really. What do you think about this question? I think the purpose of life, if it is going to end. What is the purpose of life is going to end? Philosophy. I didn't think we were in philosophy. I thought that would be done when I left university. I'm just joking. I'm just joking. Oh, there's lots of reasons. There's lots of reasons, but I mean, you just got to do the best that you can with what you have, right? One of the things that's very important to me, not to say that it's the meaning of life, but one of the things that's very important to me is how I treat the people around me and just caring for the people that are near you. So, I don't know. Some could say that was a meaning to life, but I'll just say that's something that's very important to me. Oh no. Oh, the mess of wires, the iron had to tug to get it over here. Yes. What? So, just so you guys know, there is firmware written for this project. And it's not like the finished, everything works, we can test the full suite. So we'll need to do a follow-up stream at some point. Oh no, right? Oh boy, guess we're gonna need to hop online and hang out some more. What a big... No, I'm just kidding. So that'll be really fun. But what we've got today is it should... So basically right now the way that we designed it is we've got the PID compensator that's really, closing the loop. Real-time analog control loop. For current regulation. There's another layer, so we can and do sample the signals with the micro, and then we use that information. Wow, I literally built 2 of these boards and only have the power supply modules to power one of them. That was silly. DC converter, plus minus 15, 2 watts. Plus minus 15. So this one goes, what am I doing? This one goes on the edge of the board. So plus or minus 15. And the 5-volt converter goes in the center of the board. All right. Get these installed. Actually, before I do, these might make more sense, these fuse clips, because these are tiny and kind of a pain to get lined up. Make cool electronics. Make cool electronics. Yeah, I mean in a super real way. Electronics can shape the world around us, and there's a lot of electronics that make our world a better place. There's a lot of medical devices and other very important devices, and it's pretty interesting to see the impact that electronics can have. It can be good or bad, maybe a little bit of both, but I like that. Alright, so I'm going to need to boost up the iron, extra heat. Hopefully I won't melt the table, because I don't know if any of you noticed we're on a folding plastic table. ESD! What's that? Hope I don't melt the table, though. It's possible. Alright, pin the second. on now. It'll be like that. These have got big thermal connections to the plane, so sweet. That one's done. So these are just little, I think it's 10 by 20 or 5 by 20 millimeter fuse holders. Nothing too crazy. You can just buy the cartridge fuses and drop it in. That's how we decided to implement reverse polarity protection. Simply because there's the trade-off between, it's like if you add any kind of FET or diode circuit, you're going to add a pretty significant burden voltage. And that'll prevent, or that'll limit the maximum current we can achieve at low input voltages. It's like, well, I want to make sure we can still get decent performance. What? The best IC for low power, symmetric power supply. Yeah, I mean, honestly, a great way to do something like that, Muhammad, is use a transformer-based supply, because then you can have two windings, and the oh man, words are hard. What is the word that I'm looking for? It's like flux balance, but that's not the right word. It's comments help. I'm blanking on the right word. But basically, it's like the power coming out the positive and negative half of your square wave if you rectify it. We did it for our full bridge to make a symmetric. It's basically a positive negative 120 volt rail that we were pulling a few hundred watts out of. And it's going to drive me nuts. I'm going to wake up at 2 a.m. and I'm just going to be like, that's what it was. But that's okay. That's okay. Okay, so we got the fuse clips installed. We're going to do the power jack and the USB port. So all kind of clips in nicely, so it'll hold itself in position while we solder it in place. Now, I'm trying to remember which one of these boards we had the better luck soldering. Soldering the op amps. I think sorry, not op amps, I'm going to say it was this one on the right. I'm going to say it was this one. This one has less like flux residue. So we'll full commit to this board. Put the power modules in. If we need to replace them, we can get them out and put them in the other board. But okay. This is where if I had some Kapton tape, that'd be pretty sweet. Kapton tape's a great way to hold in some things like these clips, like these power modules, like ports. Oh man. Center tapped. Protection, crescent. Yeah. Normally open. I like that aside. Power supplies are hard. It's kind of like, almost in a way, you're answering that question of, why do people still need analog electronics? Yeah, they're taken for granted, but they, yeah, they're important. And it's one of the things that we try to explain on the channel is like, there's a huge difference between building something that works when you build one and something that'll work if you build 1 million. And that difference is very important. Difference is incredibly important. Okay. So I'm gonna solder in the barrel jacks next. Oh boy. There we go. Looks great. Yep. Yeah. Ooh-wee. Just about done. I suppose it doesn't really make sense to solder the USB port onto the board that doesn't have the FTDI translator. But, guess we're doing it. Maybe I can use that board, because this Teensy does actually have onboard USB. So it will be possible to just use the onboard USB serial. Maybe that's something that we'll do on the boards that don't have the FTDI translator, because that was kind of a move where, you know, it's almost running against one of our design goals, because one of our design goals was that wanted to keep this thing as cheap as possible. Granted, there are cheap USB to serial converters, but this isn't one of them, just because I wanted it to work. And FTDI is a big company. So I'm like, if I put an FTDI part on this board, I'm going to solder it down, plug it in, Windows will automatically install the drivers, and it will just work. I'll just magically have a serial port where, you know, if you're using a microcontroller, well, you might need to install some special driver from that microcontroller vendor or something. It might not just be plug and play. Sweet. USB ports, power inputs, power modules. I'm the one that's getting them. We are, yeah. So we need micro, display, and we're just, yeah, that's it. Heat resistant polyamide tape. Yeah, that's usually what I have. It's like the orangey polyamide film. Okay. Come on now. These are nothing special. These are just a couple. They use the SSD, I think 1306 controller chip to light up the display. Just trying to get it vaguely straight. We'll see how well I can do. Gotta try to hold it straight while I'm soldering on the other side of the board. This is one of those need more hands moments. How did I do? That's pretty crooked. Okay, let's try that again. How did I do? Oh, that's way better. Okay. Oh, goodness. Yeah, please. Yeah, there we go. A little bit of solder. Oh, boy. That was maybe a little too much. How did I do? That's really crooked. That's really crooked. That's not too bad. Okay. Just get these soldered in. Yeah. The reason I went for this display is because it's got a lot of drivers. A lot of people use them. They're cheap. And you can cram a lot of information onto these displays. Like a shocking amount. Because if you use them with the 1x text scaling, sure, it's a little small, but I think you can get like 7 or 8 rows of text. That's just awesome. So you can get live readout of power, voltage, current, resistance. Excellent. So we got a couple FETs. And we got a couple headers. So ideally, you might have headers that line up perfectly. In this case, we're just going to cut them. Cut to size. So if we need to swap the micro from one board to another, we can. I might be curious, it's like if we were to make a final version, either move to something with castellated holes, so that's where you get the side drilled holes, you can solder them like a surface mount part. That could be a neat idea. Just put a paper, heat resistant, specific book or website. Yeah. Muhammad, great question about the where do you find like learning resources? And that's hard because I'm just gonna be totally transparent and like I think the easiest, best, whatever word you want to use, the one of the best ways to learn is just by building things. And you know, there's a lot of theory in electronics, and there's a lot of best practices, and some of the learning that needs to happen is learning which of the best practices are hard rules and which ones are more guidelines. And it's hard to gain that type of understanding without trying something. So I think the best way to learn is just through experience, through projects, through practice. Though you do need to understand the theory before you can do that, but there comes a point in electronics where you realize that physics is physics, and all of the electronics must obey physics. It's like when you have that fundamental understanding, and that's where I left university, is like with that fundamental understanding. And then it's like you can apply it to a lot of different circuits. So it's like, I don't know if there's a particular circuit handbook. It's more of a, yeah. I don't know, that makes sense? Yeah, IEEE is good. IEEE is good. Yeah. Learning through experience is really valuable, though. It's hard to replace experience with papers. It just doesn't always have the same impact. Yeah. But both are good. You need to study, you need to practice. Both are good. Maybe a good way to put it is like, you know, it's like when I was designing this board, when I was designing this project, it's like I'd never personally designed, gone through the analysis, tried to find a solution for a linear FET driver. But walking into that design challenge, I already knew the nature of high gate capacitance FETs. I already knew the nature of op amps. And it's kind of like, well, there's going to be these real effects and these parasitic effects that are going to be a problem. And there's going to be these other real effects or parasitic effects that are going to help us out. And it's just kind of putting the right pieces together so that you're you end up with something that hopefully works. If that makes sense. Yep. But if you're looking to learn something, Muhammad, if you've never made a circuit board before, let me tell you, that is always a learning experience the first time you do it. Because there's just tons and tons of details, like what trace width do you use, and what kind of surface finish do you need, and how do you make sure the board's manufacturable, and all those things, man. It's a journey to build your first board, but you learn a lot. So that might be something you can do. Class B AB amplifier for my driver. Yeah, that's fair. It's like just use the I don't know if you meant like use an audio amplifier IC, because you probably could use an audio amplifier IC for something like this. But I think this is a Class A amplifier? I think that's what this is. Because it's no. It's not a Class A. Is it? Is it just a Class A amplifier that doesn't have a normal steady state output current? It might be, because it's just pure analog. You got the whole bus voltage. No. I think maybe it is. I'll have to look at those topologies again. Because I know A and AB are very similar, but AB has small tweaks to make it more efficient. I think it's a variable bus voltage, but then that's, I don't know, Class H is kind of okay, I'm getting excited. So I suppose it doesn't really make sense to put the heatsink and the FET onto the board that's not going to power up. So I'll save us the time of that, do that when I've got the extra power modules. We'll set this board aside for now, and we'll focus on the one that is fully assembled. We won't put that in. What we're going to install now is the heatsink, and I need to grab the thermal pad. Whoa! Thermal pad. Okay, so got this giant sheet from DigiKey. We're using a layered material. It's let me see if I can zoom out so you can. It's A14692-30. And that material, it's really, really thin. It's isolated. Up close image of your layout. Sure thing, Jacofi. Sure thing. Let me just take a little bite out of this. I seem to have misplaced my scissors. Oh no. How do you misplace your scissors? Oh, there it is. Okay, this is nothing too crazy. Basically just need to cut it. Probably should handle this with gloves so you don't get your nasty skin oils on there and mess it up. That's okay. I'm gonna kind of oversize this intentionally. So yeah, this stuff is super thin, fiberglass centered, and it's got some kind of pasty, I don't know, it melts basically. The fiberglass maintains your spacing and your voltage standoff, your voltage insulation. And then the whatever is held in that matrix is what flows to really conduct the heat well. And we've got the heatsink. I suppose I'll give you a close-up of the layout. I'll spin 90 degrees, and if it helps, we can crack open the layout file. So we'll focus that up. It's nothing too crazy. That's the front side of the board. Yeah, it is push-pull. It is push-pull. Could be Class B. It doesn't draw current all the time. Rotor encoder. You want a initial speed. Huh. Yeah, it depends. That's always kind of a problem. Whenever you have sensitive analog stuff or small signals next to high power, high current, that's always going to be a challenge. But hopefully this helps the request for close-up of the layout. Got the heatsink. Using a little something from Omite. Now, MOSFETs, particularly the gates of MOSFETs, are especially sensitive to ESD. I still don't have a static safe workstation, so I don't know what I'm going to do about it. I guess I'm nervous about it. I'm going to intentionally not touch pin 1 because I know that pin 1 is very sensitive. And I've got a couple camming clips for locks the FET in place on the heatsink. Okay. So to get this kind of assembled right, we've got to put the thermal pad front and center, the camming clip, kind of prepared. This is just being lazy. You can get the parts out once they're installed. It's just a lot harder. You see how I said I was going to very intentionally not touch pin 1 and literally just touched it? Well, that's alright. You win some, you lose some. And we're going to get ready to install that. But I need to sit down. Yeah, I forget who it was. Mohammed, was that you? Somebody asked about common mode filtering. Someone in the channel asked about common mode filtering, and I cannot remember who it is, and for that, I'm sorry. But somebody was asking about it, and so common mode filtering would help to prevent, if it was coupling back on the wires, even just using twisted pair could help a lot if you're not using twisted pair wires. Because you can have currents of nearby wires or traces on a circuit board. That I'm just trying to get the board reasonably flat. So the heatsink lines up well. And then lots of heat. Solders into the board. There it is. And so when you twist the wires, basically you make it such that for every twist, whatever voltage or current is induced, there's an equal and opposite one. induced in the adjacent turn, so if you're not using a twisted pair wire, it could help. Alright, so now we've got the heatsink approximately ready to go. See if we can get that in focus. Yeah, it looks alright. Sorry about the lighting not being perfect. But so we're going to try to line that up as best we can. Flip the clip, which will lock it in place, and that applies nice even pressure on the back of that part, holding it to the heatsink. And this interface material has very good performance. I've used it before, love it. So I'm hoping it will keep our part cool today. And actually, that brings up a really good point. There's something that I haven't said, but we're going to have kind of an adventure together today. Because, see, I made a little mistake. Really small, really minor. Remember what I said about making this thing really manufacturable and trying to use all parts that could be assembled? Well, actually, it turns out every single part that is surface mounted on this board could be and was assembled by JLC PCB, except for one part. It's not really important, you know, it's just a part. It might be the current shunt resistors, but fear not, because we will test this design today. Basically, I've got a whole bunch of wire, and we're just going to pass some current through the wire, find how much of it makes 50 milliohms, tack it onto the board. That's how we're going to test the 50 milliohm shunt for the current monitoring. It's going to be terrible. I've got the part on order. It'll be here soon. It'll be here for the next live stream for sure. I just made a mistake. Thanks for the close-up. Tidy without too many views. Yeah, no, it's not too bad. It's not too bad. Coupling through the metal shaft. Yikes, that sounds bad for more than one reason. That sounds like that could be like wearing out your bearings and stuff. Yeah. Okay, so I think it's time for the first power on. I think we're ready. So before we go ahead and do that, we're just going to do a couple ohm checks. Make sure that it seems like everything survived. I'm just going to measure the voltage, or the resistance between the 12 volt input and ground. Few kiloohms. Oh, sorry. Oh boy. There we go. Gonna measure that resistance. It's a few kiloohms. We're gonna do the same thing for I believe that's ground. So that is, yep, the output of that. Inverter. Output of that LDO, great. Output of that LDO, super. Now we've got the plus or minus 15s. Just make sure we don't have any shorts on those. Yeah, that one looks good. Come on now. Probes are slipping all over the place. There we go. That one looks good. And there's the 5 volt rail. Great. So looks like we don't have any shorts. I suppose we'll put it in volts and we'll power it on and check all the rails. Before we do that though, I just remembered we need to spin one of those resistors. because we've got a basically a population option that I knew needed to get swapped, but I just didn't DMP it when JLC assembled it. Because when I say I don't have my shop, I mean I don't have basically any of it. So I don't even have a 0-ohm shunt. So I was like, well, I still want the part. Just don't want it on the board. So I'm just going to spin that 90 degrees. The reason why is because we're using the 3v3 regulator built onto this PCB. We don't want to use the one built onto the dev board because we're powering all this external hardware. So that was just disabling the 5-volt LDO. Someone asked why we put all of those 0 ohms on the board. I guess that's why. So I could disable that LDO. Cool. All right. And boom. What? Boom. I don't think it's going to boom. I think it's going to be great. I think this is going to work out just fine. Just fine. Just got to make sure to put that in the right way and we'll be good to go. So ideally, those would be star washers because those bite into the surface finish a little more. But hey, gotta use what you got, and it'll probably be all right. I'm not gonna over tighten this. I'm just going to hand tighten. One calibrated twist. Sweet. There we've got a 12-volt power brick. I'm going to give this thing as gentle of a power up as possible. That to say, I'm going to let the power brick soft start it, and hopefully we'll see not a whole lot. A couple LEDs, and yeah, that ought to be it. So, hey, that's a good sign. Just to test the voltages present. So we've got ground, and this should be V in. Oh, right, that one was disabled. V in, 12 volts, V out, 3V3. All right, we're gonna test the same thing on the high voltage side. We've got 5 volts, as it should be, and 3V3. Let's test the 15 volt high voltage rail. We've got negative 15 and 15. Great. Those are all the rails, right? I think that's good. So, time to put in a micro and see what happens? Yeah. Alright, we'll unplug it, add the micro, plug it in. Hey, look at that. We've even got user interface. Let's see if I can get that shown. Test thing. Test thing. There we go. There we go. So yeah, so this is basically the user interface. So yeah, these are a couple Meanwell bricks. These, so I think it was normally open. Sorry, I think I was calling you No Corporation again. Old habits die hard. Normally open. These are a couple Meanwhile bricks, and he very honestly pointed out that these are probably not the best move. Like, they're kind of expensive. I think they're like $3-4. But again, this is the first prototype. I just want it to work, and so we might have a little project coming up where we try to use these same power modules. This is the MDD02M-15. Their isolation rating is higher than what we need, but they've got the right specs on paper, so we're going to give them a try. So there's a few things that should work and a few things that shouldn't, given how we used and abused this thing. So if I take a couple clippy leads, jump start the fuse, take a couple clippy leads, jump start the fuse, we should be able to measure voltage on the input. And what I need to do in order to enable that is, just gonna try to zoom in on that for you. Just jump that, and right now there's no, wow, some goober left that power supply at 30 volts. Basically just need to go into run mode. Need to go into run mode. Oh, it looks like that didn't actually solder the switch down to the board. That's a problem. Did any of those switches actually wet? Alright, we need to touch up that solder joint. Man, that was weird. It just, I can see like the ball of solder just sitting on top of the pad. That is just bizarre. Sorry about the lighting. The sun is moving. All right. And hopefully that works. Okay. Let's try that again. Alright. Power coming in. Hey, look at that. Switches work a lot better when they're soldered to the board. Okay, so now we've got a UI that moves. You can go in and you can see the screen says set. Now you can use the buttons to program your current threshold. Hold the enter button, goes into run mode. And that is really weird. How are we measuring a current? Oh, okay. Guess there was some voltage there. That's bizarre. Alrighty. But so I turned on the input, and it's set to 13.8 volts, and we're measuring 14-ish. Let's see what we're really seeing on the input. So you're seeing 13.5-ish. I'm going to cut that a little wider. Measure it here. Okay, excellent. 13.84 volts. But before we can move forward, whatever, with our testing, we need to figure out what 50 milliohms looks like when it's made of wire. So here's what I've got. I've got our power supply, our DC power supply, and we are going to take the banana clips coming from that power supply. We're going to feed it through some wire until we get an appropriate amount of resistance. I'm going to be passing 5 amps through the piece of wire. So if we want 0.05 ohms, V equals I times R. That's R, 5 amps. So we would expect to see 0.25 volts. And now the tricky thing about measuring something like that is that you need your current source, in this case our power supply, to be different than the thing measuring, because there's leads and contact impedance and all kinds of nonsense that's going to get in the way. So that's kind of where we're headed. And to assist us on this journey, I've got a whole bunch of banana clips. Omid, looks like I said good job. Well, I don't know, it feels like an incomplete victory because sure we designed a board, but I forgot to buy one of the most important parts. Okay. So I gotta let it go at some point. Gotta let it go. We're just going to put positive clip here, negative clip there, and we are just going to start adding these clips. I don't know how many wires we're going to need to get to 50 milliohms. Could just be 1. Could just be 2. I have no idea. But we'll see this climb, and when we get up to 0.25 volts, we'll know we're there. So we're at... Wow! One of these clippy leads has got tons of impedance. We don't even need one of these. We're only passing half an amp. Passing 2 amps now and 1 volt. That's cool. Alright then. Let's try just one of these. We're gonna need 2 of these in parallel? Wow. So right now we're passing 5 amps through this wire. We are seeing too much voltage. Let's try 2. Man, I didn't think it'd be this easy to make the shunt. So that's almost exactly double. I wonder if we could just use wire. Like, I've got these jumper wires that we could use. Let's try one of these. Okay. So we're gonna need to change the measurement setup a little bit. Because now you just want to measure across this wire. Yeah, normally open, that's alright. There's been a few people dropping suggestions in the comments. I just know you're one of the very, very active people in the comment section, so it's when there's good ideas, they very often come from you. But it could have been somebody else. There's a few people that come to mind. At any rate, I do certainly love to see the comment suggestions and so forth. Okay. Nope, that is a terrible connection. It is hard to grab onto this thing. I think I might need to clip on like this. Yes. This will work. 5 amps. There we go. So that's a much lower impedance. So we want to see 250 millivolts. That is not enough. So maybe we need, wait, what is that? That's about 50. So we need 5 of those jumpers in series. So our banana clip is way too much. This lead is way too little. We need something kind of in between. Well, I've got something that I don't care too much about. I don't know if you guys remember these clippy leads, but they're pretty terrible. We got some off-brand leads, and they just drive me nuts. The clips fall off of everything. We'll use this to build our shunt, and then we'll solder it to the board. Yeah, so I guess at the end of the day, even if I did forget to buy a component, at least I forgot to buy a component that is super easy to make at home. Like, resistors are just fancy wires. You can quote that on me, or quote me on that. But it's kind of misspeaking, right? They're not fancy wires. They're usually carbon or some material, or they're laser trimmed to a very specific value. This will certainly hurt the accuracy of the system. That's okay. We'll get it replaced with the real part soon. This is just a little temporary stepping stone. Alright, got the wire, got the measurement. Come on, 50 milliohms. That's closer. So that's about half. So I'll just grab another one of those clips, or yeah, about 1.5 of those, and we'll be good. Great. Man, something smells kind of burny. It's probably my power supply. Just outputting a bunch of... Oh man, I'm surprised that how kind you guys are being in the comments. It's like, man, I'm just over here trying to make a current shunt out of a resistor or out of a wire. And you guys are just like, oh yeah, this is totally normal. This is totally fine. This is EE forever. This is expected. I just want to see the thing measure current. That's all I want. Okay. So now I've got the second wire here. And now a big problem is like contact impedance. So I'm going to need to solder this together. Otherwise it's probably going to have way more impedance than we'd want. So it'll make a nice low impedance connection. We can clip it in to the system. You guys missed that beeping? So I sure didn't. Alright. Okay. That ought to get the electrons flowing. 2 wires. And now the heat will change the resistance of the copper. So it might settle into whatever final value we're going to approach, but that's okay. 2 wires. There we go. 214 millivolts. We are on the path. 1 more wire will be more than enough. And we'll need to trim it to the right length in order to finalize the resistance. So we're going to err on the side of a little too long for now. Impulse response. It's alright. See you, Dave. Lock down. Yeah. Oh, no worries, Dave. Glad you could join. We'll make sure to boil this down and you'll capture everything important. Everything's archived, so yes. Awesome. Goodbye, sir. Muhammad. This kind of death agonies. Oh, I see. That's true. That is true. Muhammad, this kind of stuff happens all the time. What am I freaking out about? What am I even freaking out about? I mean, maybe I just wanted a multicolored current shunt. Though, this really gives me an appreciation. It's like, this is kind of what we're going to be burning all that power in. And they somehow found a way to shrink that down and shove it on those pads. That is pretty cool. It's just getting the right material and handling the thermals, and it's tricky. Cool. 3 wires. Beautiful. Okay, so now we're going to test this and expect to see a little more voltage than we need. Wow, that is almost perfect. Oh, it's probably because this is a little warm. So there's 250. Come on now. Quit jumping around. Let's put this into millivolts mode. $270, $260. Okay, so we need to take maybe a couple inches off. Whoa. Oh, this flipped around. Why am I getting such a terrible grip? Let's try that again. It is literally not attached. Is that actually right? Is that only 200 millivolts? Well, you know what? That's probably close enough. As long as we know what the value is, that's close enough. So I suppose I could add on this last little bit. Might get us really close. Ah, why not? It'll only take a moment. That'll give us a second little tap. So, want low temp co? Heat will change the resistance. Yep. Kofi of the control loop. We'd love to see how quick it regulates the current. Oh, heck yeah, man. Like, I want to get scope probes. We got the scope here. We're going to get it hooked up, and we're going to test the regulation performance for sure. We're going to need to make sure that the whole system's behaving reasonably. So we can actually get a scope probe on the P, I, D, and the summing amplifier nodes of the system to, I mean, we're going to see in gross detail how this thing's working. Alright, I'm calling this done. Whatever the shunt value is, That's what it is, and we'll just apply that understanding to the rest of our measurements. So like if it's off by a little bit, maybe 10%, we'll just know that our output current will be 10% higher than we would expect. It's like overclocking. That's actually pretty close. 225. Then again, the heat might come out of that and decrease the resistance a little. So if we're at 0.222, 0.25, so it'll be at 88%. So for at 10, if it's actually regulating to 10 amps, we'll be at 11.26, and that's going to be annoying. Yeah, Nichrome. Yeah? What do you guys think? Should I take another 30 seconds and get us to the right resistance, or call it close enough? Yeah, Muhammad. So part selection on the op amps. So yeah, there's a couple of critical things we were looking for on the primary thing that I was looking at for specifications on the op amp. The OP07, I chose it because it had a relatively low bias voltage, and that was pretty important since we're measuring such a small voltage. Needed to make sure that the input offset voltage wouldn't impact the accuracy of our measurement. And then for the other one, I mean, at that point it becomes less critical because we're amplifying the signal, it becomes larger, and yeah, the other one's just a general purpose op amp. We would have needed to select something that had the ability to drive large capacitive loads, but then we made a design decision adding that buffer, which eliminated that need. Okay. So here is where it's going to get fun. Hopefully that helps. I sense, isn't that critical if you can easily change the code? Yeah, I suppose that's right. I can just change the... That is true. I can fairly easily change the code. Though it will change... So that's baked into the equation for what we set the DAC to. Yeah. Yes, so I can change what we set the DAC to. Just need to find that section of code. .78. Love it. I'm gonna guess about 4 inches. That is a very good point. Though it will affect the noise, like our ADCs are sampling this voltage directly. So if we're off by a lot, could get a little messy. But we're close, we're in the ballpark. And actually right now it would look a little better than reality, so. Alright, I clipped off a couple inches. I think this is going to be really, really close. No, not making contact with the... Come on now. Close enough. What is that? Is that within 1%? 0.256. 5.25. We're 2% out. Close enough. All right, we'll get this bundled up and soldered in. So first thing we're gonna do, because this is gonna be kind of up in by the circuit board, we need to get this kind of away from everything. So I'm gonna twist a small segment to prevent it from coupling a bunch of noise into the traces nearby. Then I'm just gonna coil up the rest to keep it from shorting out on stuff. That's gonna be kind of the plan. It's gonna be the plan. All right. I'm excited. We're about to take the first current measurement. We're about to take the first current measurement with this project. Well, assuming everything works, I guess that's a bold statement, because in order for that to really work, that means that the gate drive needs to turn on the FET, and and the buffer needs to work right, and oh boy. Okay, well, I am hoping that we are about to measure the first current. We can probably find a way to force the MOSFET on, or just like bridge it with a shunt or something. But yeah. All right. 250 milliohm shunt. Add a little bit of solder to those pads. These are tinned. All right. Let's just check those solder joints. Yeah, that looks pretty good. Gonna twist it while it gets off the board. And now we've got this giant loop of cable. Yep. 250 milliohm shunt resistor. Looks just like the ones you buy from the store. And yeah, this isn't going to be ideal. We're adding some inductance to our current shunt. Oh boy. Now I'm doing it. Now I'm really being bad. But I really don't want this to... We got all those little conductive bits, and I actually don't have electrical tape right by me. I might even need to go to the store to get some. Okay, let's just make sure that all those conductive bits are not lined up with one another. Yeah, that looks about right. And do I have a twist tie around here? Nope, but I got a wire. So I'll just bundle this up. All right, that's not great. And yep, cannot wait to get the correct component in. But hey, it'll get us through our testing for right now. Oh no, the screen's frozen. Thank you. Oh. I'm really sorry about that. Hello, hello. We're back. We're back, John Ward. Appreciate you. Okay. Fan of the power supply. Oh, yeah. When you shut it, that thing's really noisy. It will kill the inductance. Beautiful. Okay. So that actually brings up a really good point. You mentioned annoying fans. Should probably add a fan to the heatsink, eh? Yep. So long term, we're gonna need something. We're gonna try to burn a lot of power in this FET, and that power needs to go somewhere. Hopefully, it's into the heatsink, and out into the room. But that is not going to happen on its own. So we're gonna give it a little helping hand. Alright. That's how you know we're getting serious. And it's like, yep, this is about to be hundreds of watts burned in a part. It's like, it's time for the heatsink. It's time for the fan. And I don't have any of the right screws to really attach this. We're just gonna... It's fine, okay? It's just fine. Maybe it's not. We'll find out. Okay. Holy cow. Okay. So, it's real now. It's happening. Alright, I've made an utter mess of my impromptu shop. Let's zoom in, I guess. It's about to get real. I need to take off our clippy leads and install the real deal. Power and ground. And what do we have? Our currently set to 5 amps. Maybe I'll set that a little lower. Let's try 2 amps or something for the first test. Just in case. I think our FET can withstand that forever. So we're at about 10 volts, 2 amps limited. Sorry about the fan. Okay. Soldered on fan. Pure beauty. Yeah. Got the current shunt of glory. Got the fan. This one's not too bad. Yeah. It's the connector kits in the box of old shop stuff. Oh my goodness, I'm a little scared. Okay, we're gonna go to current, and we're gonna set this to 1 amp. Current regulation is the only mode that currently works. Everything else just turns off the output. So I guess we'll see. This will test literally everything. Got it down to 1.000. Let's cut it on the screen for a moment. 1.000 is what it's set to. Okay. Turn on the output voltage. We're at 8.6 volts. Just gonna hit run. Alright, current's all over the place. The voltage is spot on. Okay. I guess. There's not a whole lot of current flowing. Guess it's time to break out the oscilloscope. But before we do that, let's test the the easiest net to test on the high voltage side. Let's test the DAC. Let's just make sure that the DAC is outputting a voltage that makes sense. So we're gonna hook up our negative probe, the banana jack. Let's test. I think you can see the DMM. Yep. Should be ground. Nope, that's the 5 volt. That's ground. Okay. So the DAC output is pin 1, which connects right there. It's set to 300 millivolts. So we should be regulating to 300 millivolts on the oh no, there's some 300 millivolts on the no, there's a resistor divider. There's a resistor divider. How could I forget? We're regulating to this voltage. We're regulating to 50 millivolts. Okay? And let's test the gate drive voltage. What are we driving the gate to? We're driving the gate to what? -2 volts. Okay. What's the input to that circuit at? 2.66 volts, huh? That doesn't make any sense. So we're requesting 2.6 volts. We're getting... Oh. Wait, what? Inverted. Oh no. Is one of these parts in the wrong spot? Oh boy. Do I have like a PNP and an NPN flopped? Oh boy. Okay, let's take a look at this schematic. It looks like I've accidentally built an inverter. Not that 2.6 volts is the right voltage anyway. But, yeah. Alright. Okay. Okay. Oh. What do you guys think? See anything obvious in the schematic or anything? Should look pretty normal. Heatsink's nice and cold. Okay, what do you think we should do? Do you think we should try to figure out what's going on with the gate drive? Or do you think that we should try to dive into the schematic and figure out why our buffer's accidentally an inverter? What should we dive into first? I'll pause for a moment so you guys can sound off in the comments. And just because I know there's a delay, I'll drop that question in the comment section. Oh, let's figure this out. One step at a time. We're close. Oh, we're close. Man, it couldn't possibly be our current shunt, because that's perfect. Oh. I don't know, Muhammad. Maybe. Maybe the BJTs are right. I hope the BJTs are right. Okay. I'll start pulling up the details. They trace through the circuit, gate drive? Yeah, it's a good thought. Okay. Yeah, there's two things that I want to get pulled up. The simulation and the schematic. Because we simulated the whole thing and we saw that it was working. And if now we build it and the behavior is radically different, perhaps we just made a mistake when we were capturing it. That is possible. Okay, drive. Okay, LT Spice. Still have it on the simulator. John Ward. Not 100% sure. I mean, like, I still have the simulation. Or you mean like I still have power applied? Yeah, I know there's still power applied. Okay, so this... Alright, ready to switch over. Look at that. Okay, so we've got the schematic. I'm gonna click into current regulator. Here's our buffer. Oh, it could be the clamp circuit. The clamp circuit could be interfering. That would be worth investigating. Perhaps there's something going on over there. But otherwise, man, that fan does get old. I don't know if you can hear the little fan that's supposed to be keeping the heatsink cold. I might need that to switch. I'll just turn it off for a moment. Okay. Just taking a look at the design. We've got plus 15 volts, 10K to the base. Yep. Little resistor on each side. 3906. And then the 3904, 15 volt rail clamped. That looks correct. Huh. That looks about right. That looks about right. Alright, I'm going to pause for about 5 minutes. I'm going to think about this for a little bit. Sound off in the comments what you think. We will be right back. 5 minutes might be a bit much. We'll call it 3. 3-minute intermission. Let's think about this together. See you, No Corp. It's a pleasure having you. Yeah, it's definitely late. Hope you get some rest. I know you said you're going back to night shifts or something of the like very soon. Or no, day. I forget. Either way, you need to be awake for work at some point. That means you cannot stay up all night. That's all right. It's all right. We'll talk soon. We'll talk soon. So yeah, coming back to the simulation here. I guess the thing that seems most likely at the moment is the clamp. And I don't know why. So I just want to test on the other side of that resistor. I'm just going to find R225 and check out what's happening. Because what I'm expecting, right, is like we're seeing no current on the output. And that means that we would expect to see 15 volts on the gate drive, right? And if it's not getting to the gate, that's one thing. But I would expect the output of our controller to be railed to 15 volts. And if it's not railed to 15 volts, that means the integrator is probably not working. And regardless of the clamp, regardless of the buffer, that should be happening at this node right here between R224 and R225. So that's going to be my play. That's going to be the first place that I think we should look. Let's do that. I'm still believing that we will end this stream victorious in some regard. I suppose we powered it on. The power supplies work. We're measuring voltage. The ADCs, a lot of it's working. Could be an analog issue. Actually, it could be an analog issue. Full transparency mode, I built one of these off camera. So if we need to switch boards, we can switch over to that one. Okay. Let's find, what was it, R224, 225. Coming in, we just need to set that to more than 0 amps. Alright. And R224 is right there. R225 is right there. So this is the node that we are looking for, though. Seeing negative 470 millivolts. What? Might be on the wrong side of that pad. What are we seeing over here? $25 millivolts on the output. Alright, let's check the error signal. What are we feeding the compensator? We want to check the node that connects R208 and R210. R208 and R210. So that looks correct. We're getting 350 millivolts of error. Positive. And that makes sense because our set point is less than the measured current. So, yep. So right now we're seeing 359. If we take this out of run mode, we would expect to see that net come down. Alright, that could be a code bug. Basically, I'm going to program this. Oh, wait, we're still in run. There we go. Config. Set. We're going to crank that up. We're going to hit run. Hopefully we see a different voltage. 388. I don't. We're gonna turn that down real low. Yes, okay, yep, so low current, low error, high current, more error. That is exactly what we should see because we're changing the set point. Higher the set point, higher voltage, higher error. Great. Hello, WTP Gaming. Welcome, welcome. Hello, Seif. Oh, man. So we're just debugging this, got it assembled. Man, you got perfect timing, WTP Gaming. Like, you just show up right after it's assembled, and it's like, man, let's go, let's test it. 100%. Full send. We'll get it. We'll get it. Okay, so the error amplifier is behaving as expected. That's the OP07. We've confirmed the correct signal there. Okay. So let's check our P term, where we would expect to see a gain of 2. So right now we are seeing 3638 millivolts. So we'd expect to see about 70, 80 millivolts on the output. And we're looking at R214, or pin 7 of our IC. Where's pin 1? 1, 2, 3, 4, 5, 6, 7. Whoa, but we are inverting. That looks like 1x error. That... Oh, it's inverting. Sorry, non-inverting means you double it. Inverting means you just invert it. Sorry, brain fart. Brain fart. So we go from positive 38 point... Is that even 2 the millivolt? Close enough. 38.6. Negative. Yep, that's pretty darn close. Okay. P term behaves reasonably. I term. We're looking at pin... What is that? Pin... just flip over to the schematic. We're looking at pin 8 or R217. R217. C216? Is that right? Yep. Well, there's a problem. Why'd we stop at a volt? That term should keep going. If this is a capacitor... What? Is our capacitor that leaky? This is just like passing DC current through it? No. That'd be ridiculous. It's got the air coming in. Alright, here's what we're gonna do. I'm gonna try to hold this while pressing buttons. Take it out of run mode. It's in config. Cool. I'm gonna try to crank up that current. Oh. Okay. I admit defeat. Set. We're gonna crank this up to about 10 amps. And before I hit go, I'm going to put my oscilloscope... Actually, no, this is an oscilloscope thing. This is not a DMM thing. This is a scope thing. Because I want to look at the AC response, right? I want to see if it's a vaguely triangular ramp. It should be a constant current capacitor charging behavior. That is what we should see. Will we see it? No idea. Thankfully, we got these great binding posts that you can kind of clip into with your lead. Never mind that loop area. Alright. Okay. What are we set to? 100 volts per division. That is a little bit too much. And actually, let's test the view. Oh, the screen froze again. Sorry. Is that better? Yeah, yeah. Okay. So now you can see the oscilloscope. Sorry about the white balance, but hey, at least it's in focus right now. That's brilliant. The struggles of pressing buttons. Oh, sorry guys. Teletronics, welcome. I am flattered that you say this is your favorite channel. I hope it's true. I do my best. I do the best with what I have. Tom, hello. Sorry about the video stuck. Struggles EEV block audiobook. What's that? That was a joke, of course. Dave is, I love his work. Yeah. I think there's some things about what we do here that are definitely like inspired by, at least in part, by some of Dave's work. And there's other ways that I think we're different, and I'm happy about those differences too. So it's like, yeah, everyone's gotta have their own style, you know? Okay, we're gonna scale her down to 1 volt. Let's be ambitious. 2 volts per division. Horizontal scale. We want... Yeah, that looks good. What are we at right now? Are we positive? Are we negative? What are we? Okay, so we're a little bit negative. And we're going to bring our cursor down and trigger a little wider. 50 milliseconds per division. And I'm going to single shot capture the falling edge. Oh, come on. Just want to single shot capture the falling edge of channel 1. Okay. Let's give it a shot. I'm about to hit go. Huh. We did not get there. Okay. Let's go run mode. See what we see. That is weird. So it almost seems like the integrator is behaving like it's not an integrator. That's pretty bizarre. That's not great. I'm just going to modify the set point and see if we see it move. Hopefully we do. That'd be kind of weird if we didn't. So right now we're set at about 10 amps. We're going to turn that down to 2.5. Hit run. It did change. We're going to change that down to about 0. Hit run. Didn't change much. Interesting. Very interesting. So the output of this circuit should be R217. Which should be connected to C216. Yep. Interesting. So this is the sum of all error. That is the I term. This is the D term. Let's see if we can capture the D term doing its thing. Gonna crank it up. Gonna move our set point. Trigger, falling edge, single. Go. Hey, look at that. So did the trigger. We see that when we apply the set point, there's all of a sudden negative error because, yep, and if we run again, no. D term? Oh, come on. Why are they all behaving like P terms? Are these caps just terrible? Oh, wait. That was the wrong net. That was the wrong net. That was the wrong net. That was my fault. I probed the wrong net. 218. Our 218. And the output is, yeah, that's the, here it is. Okay. So I almost wonder. Okay, let's try that again. Hey, it may be noisy, but that D term did D term stuff. Alright, let's turn that back up. Let's see if we can get a more reasonable pulse on the rising edge. Oh my goodness. No. Alright. But at least it's behaving approximately correct. Zero error most of the time, except for when we give it a stimulus. P term's behaving, so it's really just the I term. That is bizarre. That is bizarre. Bizarre and not terribly convenient. Okay. Let's think about this. What are the things? Let's compare this design for the implementation to what we had simulated. Let's try to figure out what's going on. So what we observed is there is an error input. That's at R210 and or R208, and the integrator is quite simply not integrating. Potential causes could be leakage current through C216, causing it to behave more like a resistor. Let's see what kind of impact that would have. Yeah, it could be, John. Unfortunately, I don't have any other ceramics except for what I have here. But just to, so I wanna play with this. It doesn't mean we can't do anything, because we do have other boards. We can steal other caps. I just want to add a parallel resistance of like 1K, and I want to run the sim and see what happens. I want to see what kind of impact that has, because if that gives us the same behavior that we're seeing, then that pretty much tells us right there that that's what's going on. It still looks... That still looks pretty good. So that would need to be a pretty leaky cap. Let's try 100 ohm. 100 ohm still has that trapezoidal ramp. Oh wait, no, it doesn't, because we're feeding it a trapezoidal stimulus. Let's feed this a constant stimulus. None. DC value. 0.15 times 5. Nope. We need a 1. So that should be 5 amps that we're regulating to. Okay. Now let's check the current. What? 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 No. Do you guys see what I'm seeing? Hey, wait a minute. That's exactly what we're seeing in real life. Hey, maybe it is a leaky ceramic. Alright, let's get rid of that parallel resistance. Hit run. And now it works. Ooh, John. I think we might be onto something. Okay, so that works. Let's find the limit. Let's replace that with a 1K resistor. Yep, look at that. 1K is enough leakage current to make that not work. That'd be a pretty crappy ceramic cap. Yes, sir. I see that. I wish I knew how to pronounce your name well. I'll say Jigyashu? Oh, man. I'm sorry. Respect from the U.S., man. Pleasure to meet you. Okay. I think that we have a probable cause. I think it's probably a leaky ceramic. Just to be curious, let's replace that with a 10K. So now we're leaking couple hundred microamps. Is that enough? No, we're still not able to regulate. Well, that's not great. Let's see. How can we fix that? Do we just need to get rid of this resistor? What if we make that a 0 ohm? Does that make the leakage current matter less? Nope. That's not super. What if you make that 100 ohm? That should make the leakage current matter less. Because it ends up being, now we've got this current path. I need to enable... Yeah. So now what I'm looking for is, what tweak do we need to make this work? And it looks... Man, that is pretty nasty. I think it's we need a bigger cap and a lower input resistance to get there. Yikes. Okay. So that looks like a point of design improvement. But I wonder if we could replace that with like a 1K, because that'll add some series. Hit the leakage. Yup. Still not really regulating. Oh my goodness. I wish I would have done a sensitivity analysis for that parasitic effect, because wow, we are sensitive to that. Like, that is the difference between working and not working. Even 100K. $100K is enough to throw off our set point. That's like nothing. That's 20 microamps of leakage. That could even be within spec. That's not even a failed SMD component. That's just a cap. Granted, it's leaking 20 microamps with, what's the voltage applied? Yeah, 2 or 3 volts. So it's possible we might be able to help by cranking up the gain on this buffer. Oh my goodness. That is crazy. Okay. So what are we going to do about it? Let's take a measurement. Let's measure the voltage across this capacitor, and then we can capture, we'll measure the voltage across it and the current through it. So if we measure the voltage at R44, we can measure the current through C3, and then we'll measure the voltage across C3, and then we'll be able to figure out the effective DC resistance of that cap. It'll let us know if we think the cap failed or if it's operating normally, and it'll let us know how much current we are leaking. Stinking ideal capacitors in LT Spice. Okay, so we need to find a capacitor. Yeah, could require a super low leakage, something or other. I mean, like I said, we're just using bog standard, bottom of the barrel, get it from anywhere type of parts. So we're looking at R209 and C216, and I've got a feeling we're gonna need millivolts range on the DMM. Yeah, there's a schematic linked in the description. Make sure to check that out. P-term. Okay. So the voltage across this cap is overload. Whoa! Got volts across the cap. So we've got 1.7 volts across the cap. R209. Oh wow, yeah, so there's almost no current going through that cap. And I'm measuring so the error in is 555 millivolts. The current is almost nothing, which makes sense because we're looking at microamps. I don't really know how to measure more precisely because I don't have a microamp meter. But we're only able to get up to 1.5 volts. So that's interesting. So we're seeing 500 millivolts in, -1 volt. How does that even make? Oh, because we have a positive input. Yep, positive input. 1.1 volts. I feel like I'm missing something obvious. Let's try to capture that transient with the scope one more time. Let's just try. Okay. And we are set to falling edge trigger. So we're going to turn this down to very low current, 0. Gonna hit run, and in theory, integrator's still where it was. Let's try a power cycle. Alright, integrator's down to nothing. I'm sorry, what? I'm sorry, what? I'm sorry, what? So now we're up at like a reasonable voltage? What? Okay, let's capture the power on transient, I guess. Let's see what's going on. Let's try that again. It triggered, but I don't really see anything. Okay. So, no, none of that. That's not what we want. That's what we want. So this is the power on transient. We're just kind of meandering our way down. Doesn't look anything reasonable. And now I guess we'll try a rising edge trigger. Single shot capture. Give this thing a set point. Hit go. Run. No, we're still right down there. So it's kind of like we just boot up to wherever, and then the system does whatever. That's not great. Woo! I suppose we can try. Yeah, let's just see if it's a bad cap. It's about where I'm at. What do you guys think? You guys agree? Yeah, we're seeing 15 volts. I mean, we can check. Let's just check to make sure they're nice and low noise. So we didn't hook it up to the oscilloscope. Could be possible they're noisy. So that's worth a try, worth a check. That is for sure. This should be one of the rails. So, yeah, that looks pretty darn good. 2 volts per division. Wait a minute. Wait, what? Hey, You're a smart guy. That ain't right. That ain't right at all. What is gulping so much power on the 15-volt rail? I wonder if it's our transistor amplifier. Are we browning out the rail? Well, that'll do it. Oh my goodness, that'll do it. I suppose, yeah, when you check your supply rails, and then you try to turn it on. Alright, DMM, volts range. Yes, we've got a separate supply for the digital stuff and the analog stuff. Yeah. Negative 4 volts. Positive 4 volts. Yeah, that's not right. Let's try turning off the output. And let's check that again. 4 volts, 4 volts. Okay, let's try that on a fresh boot. What is taking all of that power? Still 4 volts. 4 volts. Interesting. Okay. Well, that gets us on the right path. I'm gonna guess it's our transistor buffer. What do you guys think? Because these can't really output much current. So. Yeah, it's pretty low output current, but that should be enough. Because basically, ideally, our transistor buffer doesn't pass steady state current. Ideally, just charges the FET gate, so it would have a gulp of current, and then it would come back. Alright, let's test the voltage. There's a couple transistors, so our gate drive could be browning out the 15-volt supply. Good theory. Just might work. And if there's one place that was bound to do that, that would be... I've seen it power on correctly when we're not trying to drive the gate. So that could very well be the whole problem right there. Okay, so R241 and 242 will reveal the problem. If there's steady state current passing through those resistors, that means we got BJTs fighting each other, and we're burning out the supply right there. And look at that. Yep, steady state current through that resistor. Okay, so we're going to need to increase the resistance of our gate drive amplifier a little bit. That's easy enough. That will hurt our transient response, but it just might let us get this supply turned on. Alright, that's a step. That's a big step. That is a big, big step. Rather than stealing parts off of the boards that we've constructed, let's delegate one of these. I think there's one with a sticker smudge on it. Hey look, spare parts. I found some. Alright, so I think we've got some 10 ohm resistors that we can try, and we've got some 100 ohm resistors we can try. For the sake of getting this thing up and running, I suppose let's try, let's see, 2 ohms browned us out to 4 volts, so 4 volts, 2 ohms, V equals I times R. V is 4 divided by R, so yep, so that's about 2 milliamps that we were shoving through. So now if we replace that with a I times R, 2 milliamps times 10 ohms, that should let us go up to about 20 volts current. Everything else held constant. So 10 ohms should be enough. Let's find a 10 ohm resistor. R0. There are a couple 10 ohm resistors hooked up by the USB transceiver. That is R108 and R104 in the schematic. Found them. Let's harvest them off of this PCB. $10 ohm resistor. So yeah, that'll limit the maximum gate drive current, but it will also limit the steady state leakage. I wonder why that is. I wonder if it's because our transistors are a little mismatched or what. I'll need to investigate on my own time, but I won't make you guys come along for the ride. But that'll definitely be in our summary video, so we'll have a summary of all of the testing and bring up and all that we release. So make sure to get subscribed if you want more details on what went wrong. So I just added a little bit of solder. Then I'm going to come in, bridge across. I now realize you may not be able to see what I'm doing. Oh no, you definitely cannot. Sorry about that. Okay. I've got the resistors scavenged. I'll show you what I did over here. So the 2 parts we need to replace are over yonder. It's these 2 parts right here. I'm gonna come right in with the iron. I'm gonna just add a little bit of solder to both sides of these resistors. It's just to make it easier for the next step. That is the whole reason. We don't really need that solder. Then I'm gonna get the tweezers ready. Bridge across both terminals and just sweep the part off. Get it out of the solder blob. Oh, look at that. These parts came right out. Alright, now it's time for the replacement. Just going to clean off some of that extra solder. Come in with the new part. Check for solder bridges underneath. Looks good. And that giant heatsink right there is, how do you say, not ideal. Kinda in the way, almost. Oh my goodness. Just trying to grab it with the fiddle. Okay. That part is kind of in the right spot. Yeah, note to self. Heatsink is in the way. Oh man, this could be it though. This could just snap into operation. Because if our op amps are browning out, everything's browning out. Oh boy. And the reason why we wouldn't have seen that before we added the current shunt is because until we added the current shunt, we couldn't actually pass current into the gate. Though now that I think about it, I did not check the gate leakage spec of this part. It's possible our FET just needs more power. It's possible that it wasn't actually the gate drive resistors and that it was actually the FET. I should have checked to see if the current was present in both of these resistors before replacing them, because that could be the problem. But we're about to find out, because if the problem is fixed, that means it was the amplifier, and if the problem is not fixed, that means it may be the FET. Either way, we are about to find out. Oh boy, looks like the camera froze again. There we go. Come on now. There we go. Yep, Muhammad, absolutely. The way that I've heard it is your first the first circuit board you make is always a prototype. But I think it's the same truth, and it's just, man, there's 1,000 little details, 1,000 little things that can go wrong. But that's the beautiful thing about using a power module. I just need to find one that fits, right? So it's like for our next, this could be the end of the road for today if we find out that we just need more current here. But we can find another module and like solder wires and get it in the design. We can do that for sure. Okay. Now let's see what is happening. Voltage over here. We've got 200 millivolts. Yep, so we're leaking straight from top to bottom. Let's see if we can. There's our 2 ohm parts. Let's check what our rail voltage is. I think it's R204. Yeah, there it is. These 2 parts are right here. What? That's not right. Yes, we're at 2 volts. What in the world? Okay, I just want to make sure I was measuring that in the right spot. So we're going to flip this over. We're going to check it at the power supplies. And pull in the DMM so you can see it. That is not correct. We are not seeing 0 volts. We are definitely seeing more than 0 volts. Okay. That's not great. So we're still seeing the problem. If anything, it is worse. A buzzer. Ding, ding, ding. Video froze. Not right now, though. We're good. We're good. Okay. Where are we going? Where are we going? What are we doing? Come back to the screen share. Screen share. There we go. So basically we're saying that we're browning out that supply. And we need to go to our MOSFET. Yes. Yes, indeed. MOSFET. Gate leakage. Here it is, pulling up the data sheet. Just gonna try gate to body leakage. That's not exactly what we're looking for. Or is that gate to body? No, that's right, that's right. It says 100 nanoamps at 30 volts. It's probably not that. Could just be the circuit. That is possible. It's possible it just doesn't work. But it's the thing that's bizarre to me about that is we powered up the board and we measured all of the rails without the current shunt installed. And it worked. Now that is weird. That is really weird. It is weird to me because there's a couple opportunities for there to be current, right? We could be dumping current through, could we? That's biased. Comes down through there. Yeah, yep, right through this path. And the other thing could be is if the parts that we put on the board have a different footprint. That could be kind of weird. All right, here's what I want to do. We're going to bypass the buffer circuit just to run a test. Yep. Muhammad, exactly on. That's where we're getting. I suspect this circuit. I want to dive into that more. So what I'm going to do is I'm going to take this R225. We're going to spin it, tack a wire over. We're basically just going to add that whole 1K. And it's going to be a really slow gate drive, but it'll be really low current. We're going to swing these two resistors, swing that resistor, and tie it over. That's going to be our play. It means we're going to be very, very limited in gate drive current. But it means that that buffer circuit won't be an issue anymore. All right. And hopefully I can just kind of swing those resistors out. Not a problem. Okay. All right. Resistor is still attached. There we go. Had that one spun. And that one as well. Oh boy. One K ohm gate drive. That's gonna be kind of ugly. That's gonna be kind of slow. We're gonna need to be gentle with voltage transients. For sure. So now if the gate is pulling current, we'll just see voltage drop across this resistor, but the 1K ohm resistance should limit it to a very reasonable amount of current. but based on the fact that we're seeing steady state current through that low ohm shunt, and that's a big red flag right there. Okay, so we've got the resistor ready to accept a jumper. Let's just grab one out of our kit here. Find one that gets us over to the gate. Just right across the whole circuit. How's this white one looking? It's a little too long. But the yellow one. We can make that work. We can make that work. Okay, gonna add a little bit of solder to our jumper wire. Gonna add a little bit of solder to our pad. I'm getting all kinds of tangled up here. Okay, looking good. Just need to bend wire tiniest little bit. Oh wait, I'm on the wrong side of that resistor. Now we're making art. Maybe we'll end up seeking a high output current op amp after all. Alright, now let's just make sure our art is functional by checking the impedance from the gate to this net, and it should be 1 kilo ohm. 0.995 kilo ohms. Okay, here goes. Oscillation proof, John. Yeah, 1 kilo ohm ought to do it. Tektronix, that's what I call a tight pull down. Where's my cursor? Muhammad, show. Yeah, it's like we're trying to solve the problem, you know? It's the same for me. It's like there's the part of me that wants to walk away, and there's the rest of me that's like, oh, but we're so close, we might be about to figure it out. And it's like you want to be on the journey, you want to figure it out, and it's just electronics, man. It's exciting. It's got that. You know, we're solving problems that no one else in the world has ever solved. Well, that's not true. We're solving a new instance of a problem that many people have solved before, but it's slightly different because it's a new combination of circuits, and it's like, yes, this module's been tested, but not with this exact circuit. So we need to find, for this implementation, exactly what is wrong. Somewhere in there. So yes, but Muhammad, I love it. When I saw your previous live streams that were like 3 hours, it's like, who in the world would watch it? But I've been here for 3 hours, so yeah. I appreciate you, man. Thanks for sticking along. I'm glad that you're here. I'm glad that you're watching. And everyone else as well. Everyone else as well. Oh, boy. Maybe it wasn't the ceramic cap after all. All right, here's hoping. Also, I need to clip something because I've noticed it twice, and we've managed to not blow up the board yet. A couple wires under here are getting dangerously close to touching because I didn't clip the leads very well. That was my bad. Is the fan wires. They're just kind of floating around down here. I really need to clip those off before they short on something. Okay. Here's hoping. Let's hope we bias that FET gate to something. Alright, we're powered on. What do we see applied at the gate? Please let it be something. Oh, that's resistance mode. It said battery. That's a sign. 13.8 volts. Hey, it was the buffer circuit. For some reason, it can be on the board, but it just can't be driving anything. So I'm guessing I've got the footprints wrong on one of those transistors. That is my bet. That's my bet, and I'm sticking to it. Teletronic says, next time I'm bored in the train, I'll take my board and soldering iron with me. You know, my soldering iron runs off 24 volts. I bet we could build a modified, like, power bank that would output 24 volts so you could run a soldering iron mobile. Or, like, charge your laptop or something. That'd be pretty cool. Okay. Okay. So, that's pretty cool. We're biasing the FET on. The FET is on. Just to check the resistance. I'm going to check the resistance on this. Just see what we get. Basically 0 ohms. Cool. So the FET's on. I don't know why. Probably shouldn't be. But hey, that's cool. Let's check the output of our integrator. That's still resistance mode. Output of the integrator is at negative 14 volts. Output going to the FET is at 14 volts. Error is at pretty much 0. Oh, that's why the error's 0. We booted up. The set point's 0. The current's more than 0. Should I be bold? Should I be bold and turn it on? So I think I'm gonna. Okay. All right. Gentlemen. The TS100. Oh yeah, the USB powered one. I'm just gonna turn it on and see what happens. Okay. So there should have been a little current transient, but there's no steady state current. So I'm guessing the gate turned off. Yeah, the gate turned off. We're right below the threshold voltage. So our compensator turned the gate down. Oh my goodness, this might work. The gate is now at 4.887 volts, and the threshold voltage is like 7 or 5 volts or something. So we're right below the threshold voltage. The current is basically 0, and the error is probably at 0. Dang, man, that was cool. So the error is probably back down at, yeah, basically nothing. The output of the integrator is negative a couple volts. Yeah. I'm not a huge fan of the smell of rosin, but, I mean, it's not the worst thing in the world. It's not something that I really go out of my way to encounter. We're going to add a little bit of burden voltage, but we're going to add an ammeter. Just add an ammeter. So our little buffer circuit draws a bunch of current. It's a pig. So yeah, we're measuring approximately 0 amps. Let's come into our configuration. Current. What do you guys think? 100 milliamps? Let's go for an amp. With our excellent wire-wound resistor. What could possibly go wrong? Okay, I'm getting distracted. I'm excited. We might have found the problem. Thank you to everyone in the comments helping me debug that. You guys are brilliant. Let's hit go. Okay. Ah! Works better if you put the current shunt in the current shunt. So, we're measuring 0 amps. There's 2 amps flowing. We hit the current limit. Why is that? Let's take a look at our system. Let's take a look at our everything. Let's see why we are not regulating to an amp. Our error amplifier is telling us, saying there's positive error. So we should be trying to turn down the output. But we are not. The gate is biased on all the way. Alright. Yep. Let's try turning the current down. Maybe it's just a set point issue. Set it down to, I don't know. Let's punch in to the, yep, there we go. Set it down to, I don't know, 200 milliamps. Oh! That had an effect. So it looks like our current ADC is either not working or is otherwise not soldered to the board correctly. We are measuring a very small voltage. So right now we're getting 0.39 amps when we asked for, what was it? What did we just set that to? Set 0.2. We're getting 0.4, so it's almost double. Did I screw up our current shunt? I might have screwed up our current shunt. Did I make it half as big as it needs to be? There's a factor of 2 somewhere. Oh, speaking of, I should probably make sure our fan's actually on the heatsink now that we're actually burning power in the FET. Hello! Danger! Danger! Okay, so let's try setting it to half an amp. And maybe that'll explain. Maybe we're just a factor of 2 off. So we'll go to 0.5. Actually, let's be bold. Let's be bold. Let's hook up the, Actually, I don't really have a good way to hook up the voltmeter to that to capture the transient response, but we'll do that in a moment. We'll do that in a moment. So we're set to half an amp. Let's see what we go to. I'm expecting it'll go to about an amp. 1.08 amps. Yeah, seems like our current shunt isn't exactly correct. Seems like our current shunt is approximately double what it should be. The TS100 seems a cool iron. Agree. For mobile stuff, if you only got USB. Yeah, so Muhammad, that's a great point. So right now the transient response of the system is going to be a lot worse than what you would expect because that 1K resistor is going to limit how quickly we can charge and discharge the gate capacitor. So if we gave this thing a fault right now, if we hit this thing with a fault, it would blow up that FET if we gave it a voltage transient, an overvoltage event, because we just don't have the gate drive to turn that FET off fast enough. Does that make sense? But as far as like testing the regulation, as long as we're really gentle and we don't give it a huge voltage transient, it'll be okay. It'll be okay. It's good for testing, but it's not good for the final state. We need to fix it, but we've been streaming a long time, so I don't think we're going to fix it right now. But I do want to test the regulation performance. So right now, we're pulling 1.08 amps from our supply. And I'm going to get the calculator in here. So we're pulling 1.08 amps. And I'm just going to divide that by 2 because I definitely have an error here. And if we turn off the system, You can see we're set to 0.5. So if we subtract 0.5, that's the amount of error divided by our set point. It's 8% error. Sorry, I was off the screen. That is 8% error that we just observed. Let's try it at a higher current. Heatsink's definitely getting a little warm. At this point, ooh, I should like tape this thing to there to keep this cool. Give me one moment. We're gonna crank this thing up to a few hundred watts, and we'll be right back. I need to go grab some tape to secure the fan to the heatsink because it's blowing itself. I set it here, and it blows itself away from the heatsink. So we're gonna fix that and get right back to it. I'm excited. Are any of you guys excited? I am excited right now. I am so pumped. I mean, even if the voltage ADC isn't working, I don't even care. Like, we have a PID compensator built out of discrete components regulating the output current of a linear FET, and it's working. Isn't that exciting? I'm excited. I'm so excited. Yep. Alright. So, there's one piece of tape. That ought to help. Going on the bottom here. Bottom of the board. Come on. That awesome resistive current shunt. I love the fact that we are measuring output current through a bundle of wire. That is literally amazing. Now we got the fan secured. That'll keep our part nice and cool. Oh my goodness, that is awesome. So just curious, I'm going to turn down the input voltage. Turn down the input voltage. And now you can see we're at, look at that, 7 volts, still regulating. 4 volts, still regulating. 2 volts in, still regulating current. 1 volt in, still regulating current. The burden voltage on this thing is decent. No way. No way. I don't even believe my meter right now. The power supply is saying we're at 0.1 or 0.5 volts. We are at 0.5 volts in, still regulating to an amp. That is amazing. Alright, we're starting to drop out. Yeah, that comes up fast. Cool. Alright, we're going to set it to, let's do 3.3 volts. Whatever, that seems like a voltage I would use. Watching this episode is like a roller coaster ride. Full on entertainment. John. Awesome. I'm glad you're enjoying it. Yeah, I am having a ton of fun as well. I'm sure you can tell. I am so excited that this is working right now. I'm so excited that this is working. I should actually, let me cut out the zoom just a little bit. I know it's nice that you can see the screen all big and whatnot, but I want to make sure that you can see the current shunt as well. Yeah. So I'm just gonna slowly turn up the output voltage back up to 3.3. Alright, so now you can see the output current. This is in amps, and you can see the display of our design. Great. And I'll just keep an eye on the thermals of this thing every now and again. Yeah, it seems like the fan's keeping it nice and cool so far, but we're only burning 3 watts in the giant transistor. But we're going to try to push it up to 10. And I've got a 24 volt, 25 amp supply. So as a final test, I think we'll try our hand at that. See how bad it can get. But this lab supply can get up to 6 amps without much trouble. So we're going to set the current limit to about 4 amps. And I'm going to set our supply up to, let me just make sure, yep, still live, don't want to miss it. We're going to set it up to 1 amp. So we'll expect to see 2 amps out. Run. 2 amps out. Great. Go back into config. We're going to set the current up to 3 amps out. Sure enough, 3 amps. So now this should push us up to 4 amps once I hit the button. I think we're hitting a... Oh no, we're hitting the current limit. There we go. Alright, so now that the current limit on the supply was rectified, we're up at 4 volts. Or sorry, 4 amps. 4 amps, 3.3 volts in. Let's try turning up the input voltage a little. Let's try to burn some real power in this thing. But let's do that at 5 volts. Or sorry, 5 amps. I'm getting so excited, I'm mixing up my units. We're going to set this to half of what we want. And so I just want to say, this is part of the reason why I didn't want to run the whole loop in software. Just because I knew that I could build analog hardware that was more precise than when you got this giant loop of the ADC and the micro and all the digital stuff and the analog stuff, and you go from the ADC to the DAC and back. It's just a lot of conversion, you know? Like, it's just a lot. So, anyways, we're up at 4.94. Oh my goodness. It's time to get some current through this thing, some power through this thing. See what this thing can handle thermally. Because this supply can output up to 30 volts, 6 amps. So you can push this thing pretty hard before we switch over to the other supply. So let's shoot for, what do you think, 10 volts? That'd be 50 watts. Let it soak at 50 watts for a while. Sure. Maybe we'll start at 5 volts. So we'll do 25 watts for a minute. And while this sits at 25 watts, I'm going to get my Unity meter hooked up to measure temperature and get a thermocouple on the heatsink. Thermals, man, they're riveting. They are just so exciting to sit and wait for something to hit equilibrium. Oh yes. Oh yes. While we're at it, I think I'll try to get the oscilloscope hooked up to measure the voltage across our current shunt. Excellent. Yeah, that's really hard to measure. I don't know if we're going to get the oscilloscope hooked up. We might need to add an external shunt resistor for that. That's okay. That's okay. Which uni did I graduate from? Can you include the NTC, PTC to measure? Yeah, so, John, that is a great question. Typically, I would include something like that, but this has got the benefit of being a piece of lab equipment, and what I mean by that is we can be pretty darn confident that you're with it. It's like you're setting the current. You are with the equipment and the device under test all the time. Like, if this thing starts to go nuts, you're gonna know. Something like the UPS project, there was monitoring all over the thing. But every monitoring function that you add adds cost, adds complexity, and I'm just laughing because I think our current shunt is heating up, and it's affecting our regulation. Because we built our resistive shunt at room temp, and now the coil's definitely starting to heat up, and the current set point's dropping. That's amazing. Alright. Getting our DMM set up. Shove that a little up there. See if we can get this. As you can see, all three. Got current on the left, temperature down here, and the set point up there. If I take the thermocouple and touch it, I have the thermocouple backwards. My mistake. Okay, let's try it like this now. There we go. Now when I touch it, it goes up. Let go, get it in the breeze, comes back down. I'm going to try to get this on the heatsink somewhere that makes sense. I wonder how the component... Oh yeah, that seems very well coupled to the heatsink. Ideally, you'd use some kind of thermal epoxy or something like that, but hey, this is a first test. This will be good. Just need to give that a chance to heat up a little. We'll be okay. So just so you can see that setup. Dope. Just so you can see that setup. Just so you can see that setup. Just got the thermocouple taped on the top. Okay. Okay. Awesome stuff. Muhammad, which unit did I graduate from? That's one in the States. I don't know. Personally identifiable information. I don't know. We'll see. Maybe next stream. I'll hold on to that nugget for now. If you're curious, this is what the scope looks like right now. It is insane. It's just noise. It's just noise. Okay. We're at 34C. That seems totally fine. Let's crank up the power. Let's go up to 50 watts. $50 watts. Continuous. Yeah, it's... You can tell it's more power. Heatsink's trying. You might need a bigger fan or a bigger heatsink long term. But I figured we'd start with this and see how far we could push it. Let's actually come in here. Just crank up the power a little more. So we're going to set it to just below the capabilities of the supply. Let's go... Yeah, so it should be about right. 5.38. pretty close. .85. Let's give that a try. 5.5. You can get a little more. 5.7. You can get a little more than that. Need to tweak the focus on this. It's focusing on the wrong thing. Oh boy. Oh boy. There it is. Should be a little better. Oh right, we're burning a lot more power. How hot is this getting? 50C? It's not too bad. I can still hold my hand on it. That's not too bad. Whoo! It's getting hot though. Whoo! That is getting hot. We're probably at about the limit. So if the heat sink's at 50C, what are we at right now? We're at 10 volts, 6 amps. .10 volts, 6 amps. Really? That's it? It's only 60 watts? That's not very entertaining. So definitely a bigger heatsink. Definitely. More fan, more heatsink. Oh boy, that's exciting. That is very exciting. Thank you all for joining this journey today. We're gonna do a couple more things before we call it. I'm gonna hook this up to the super massive 24 volt, 25 amp supply just for a moment. Maybe we should set the current something smaller with the lab supply. Yeah, and we're going to test it at higher voltage. We're going to just approach. So now we're regulating. There's 32 volts on the input. Thereabout. You can see that on the display. Got 30 volts in, about 0.7 amps out. So we can't get quite up to the 100 volts, but I reckon as long as we don't dissipate too much power, it ought to be fine. Yeah, just go ahead and... I think if I go to any other one of these, yep, so I tried to regulate resistance, and in the software I just had it turn off the output if you set it to a mode that's not supported. So that is what happened. Reconfigure this. Let the lab supply cool off a little. Yikes! That was not smart. Shorted out the lab supply when it was set to ridiculously high voltage. But so now we're going to connect the positive and negative terminal. Yep, so this will be correct. Got our leads that need to connect to the power supply. We've got a V plus and a V minus. Let's see if this thing's worth its weight. So that's just basically going to get hooked straight up to mains. It's a big old power supply. Current set point is 0. Just make sure our hopefully the gate is turned all the way off. That's pretty easy to check with a DMM. Just need to check our gate voltage. Should be nice and low. If it's not, I'm going to need to rethink this because we're going to blow that FET into oblivion if this thing's biased on. Ooh! That's up at 13 volts. That's not going to be good. Yeah, I don't think we can run this test right now. With the gate drive the way it is, basically what's going to happen is this system is... I can't really gracefully transition between power supplies because with the gate drive as weak as it is, with the 1K gate drive resistor, when we first power on that 24 volt supply, 25 amp capable, that FET's going to be all the way on, and our control loop will try to turn it down as fast as it can before the lab supply would hit its current limit and save the FET. But now, until we can actually drag the gate to where the control loop wants with that 1K resistor, it's just going to be sitting there pulling 25 amps. Maybe the short circuit output protection will save us on the supply, and it'd be a little ugly for a while. And I don't want to just blow up FETs for the sake of blowing up FETs. Figure out that buffer circuit. We'll do some debug videos and whatnot, but hey. Yeah. Okay, John. You want more power? I'll give you more power before we go, but we have to do it with the lab supply. We can push it up to 6 amps, 30 volts, but that'll be our peak. That'll be our peak for today. 6 amps, 30 volts. Yeah, it's 180 watts. It's nothing to sneeze at. It's a fair bit of juice. Alright. Power in. There it is. Alright. We'll see how long we can handle that power. I'm just going to go straight for it. We're just going to go straight for it. Or just set it straight to 3.0. There you go, pulling 6 amps. Temperature is at ambient. That cooled down pretty quick. Here we go. 16. 20 volts. 33 volts. Let's turn it back down for a moment. Let's see how she seems. Woo! That is hot. I can actually see that the part got hot because I can see that around the edges of the component you can see that it was like melting into the thermal interface material. But it seemed to handle that transient really well. This is a good FET. This is a good part. Let's give it another blast. Alright. We're down to 4 amps. I wonder why. Is our resistor heating up? Our FET is certainly heating up. Woo! I wonder if it's like a power limit or something inside the power supply. That's pretty cool though. Yeah, Muhammad. Yeah, so, you know, that's kind of the point of our overvoltage and overcurrent protection circuits. So at the very worst case, we'd have an overcurrent event for a few microseconds, triggers that fault protection, and then it'll hiccup and recover. For exactly this type of circumstance, like when you first plug in a voltage supply, like that's what that circuit exists for. That's its function. Dang, this bird's getting hot. We're at 61C, 70C on the heatsink. Yeah, that's pretty hot. Yeah, it just, I mean, I don't know what this heatsink's rated for, but it's not 1,000 watts. It's not 300 watts. It makes sense that we're hitting that. Yeah, that's cool. All 70C, I can't really hold my hand on that anymore. That's too hot to hold your hand on. That is hot. Yeah. I think it's kind of like a... So I know you're saying the thermal interface material. I think that's what you're talking about. So typically what I would expect is that it's kind of a situation that resolves itself. So, you know, the part heats up. Maybe the thermal interface isn't great. Kind of melts into where it needs to be, and then the thermal interface becomes better. So it's kind of like the first time it gets hot, it'll kind of get where it needs to go. Hey, this is a good first start. Soft air would be good, but yeah, we've got hiccup retry right now. It's just, you know, we built the buffer there for a reason, because we need that much output current. And yeah, when you go and change the circuit radically, you just get rid of it and replace your buffer with a 1K resistor. I need to go back into the LT Spice sims and really take a look at that to understand the effect on the overall system. Make sure we won't blow up our gate or the FET, and yeah, all that good stuff. Man, this was an awesome stream. I'd call this a smash success. We built a board. We burned a few hundred watts in a FET. We have a PID control loop, and I'm sorry we didn't dive in more. It took a long time to debug this, but next video for sure. There will be more on this. We'll be diving into this design a little more. We'll be pushing it to its limits. We'll update the code so we can do voltage regulation, current regulation, and resistance regulation. I don't know if you noticed, but we were calculating the resistance in real time. I never actually checked to see if the math was... Oh, no, it wouldn't be right, because our current ADC wasn't working, but we don't have the current shunt in place, so it's hard to know why that's not working. But oh my goodness, am I excited. And I cannot wait for the next one. I cannot wait for the next one. So, yeah, John, thank you for being here. I don't know if I can see everyone who's currently in chat, but wow, thank you all for being here this morning. For me, afternoon, evening, night, whatever it is for you. 4 hours, 12 minutes. That is great. It is great. That is true, Muhammad. For steady state, the gate does not require current, but to change the voltage on the gate, you need to charge or discharge the effective gate capacitance. There's some capacitance inside of the part, and so if you care about the transient response of your current regulation, you need to drive current to change the gate level. So it's not a steady state current, it's a transient current. So that's why it's exactly that inrush situation that's different. Right? So our gate voltage is charged up to 15 volts because our PID compensator is saying, hey, we want to regulate to 0.0001 amps, and we're getting 0. There's some error, so the integrator ramps up, the gate drive ramps up to 15 volts, and now it's sitting there at 15 volts, and you plug in something, and now your effective drain to source resistance is a few tens or hundreds of milliohms, and then you need to quick pull that gate back down to 4 volts or so. And it's that time while you're transitioning from 15 volts back down to 4, if it doesn't happen fast enough, that you could damage the part in that transient power event. Yeah, sorry. I might have misspoke, but that's what I meant. At any rate, this was a beautiful stream. Thank you all for being here. Thank you for engaging in the comments. Just want to say thank you to everyone for being here today. Thank you for everyone. That's not right. Thank you for everyone who joined us today. Wait, that's not right either. What? Oh, I see the problem. I see the problem. This is what I wanted to say. Thank you for watching. Thank you all for being here. Thank you. It's been awesome. It's been awesome hanging out, spending some time with you all, having a conversation. and getting to hear a little more. Thank you for everyone who shouted out where you're from in the comments. I really enjoy knowing that. I think we had New Zealand. I think we had, thank you. I think it's, oh man, Kumar is easy, I can say that. Your first name is hard. Maybe give me a phonetic spelling so I can say it better. I'll butcher it if I try, but I think we had India represented. I think we had Australia, I know we had. I think we had a few in the US. Man, it's been great. Thanks for being here. Thanks for being a part of E for everyone. Thanks for watching. And you know there will be a part 2. We need to dive into the PID compensator, the transient response. We need to fix our discrete BJT buffer, investigate why we needed to bypass that, why the current was more than what we would have expected. Germany. Yes, yes. Excellent. ZA? ZA. Is that? I don't know what that abbreviation is for. Is that AZ, like Arizona? South Africa. That is fantastic. That is fantastic. Yes, but there'll be more to come with the control and the debug and improvements to the firmware. But for now, it's been great playing with our current shunt. And spending this time, so. Oh, really? ZA is South Africa. That's fantastic. It's fantastic. Well, we'll see y'all in the next one. For now, that's all we've got. But we've got more great content coming, live stream and regular. Bye for now. Cheers. Hope you learned something great today, and I hope to see you again soon. Bye.